you should know in this session tell about what are R chords, T chords, T box, everything. Just one line if you tell that
Yeah.
this thing is used for this, and that should be enough.
Okay. So let me quickly start with an overview of what this whole SSLABS core business is.
Yeah, so regarding that coordinate thing, I mean, with respect to the blog, there's a coordinate and then there's like a global coordinate. So if you can clear that part, that'll be great. Yeah.
Okay, fine. So before that, to give a context to the people who have not used SSLabs core, let's go back to the library we were writing yesterday. Clone it. So when we left off yesterday, we were doing basics of MPI, send receive, and then we saw blocking problems in send receive, and then we went to unblocking or asynchronous communication, I send and I receive. And then we were able to pass messages across two independent processes just to bridge a communication channel between the two. And we can communicated some data. Now, that was just a simple copy toy problem. Huh? Or actually, the MPI problem was not even a part of copy. It was just one variable, one sum being sent, or one variable being sent across two processes. So if I have to send an array of data across processes, then open up my copy MPI. And just let me know if there's if my voice is lagging or anything. Huh? So we'll go to the I send I receive thing that we were doing yesterday. So this was a structure, right? You can delete this. This doesn't need to be there. So because creator, so we will see how to create blocks for any grid kind of thing, or how to structure a actual simulation code which uses grids of or a domain of grid points. Okay, so let's see, parallelize or domain decompose a grid. So we will create a merge request for this. We'll do git pull. So if we go to copy MPI, now we will quickly, just in 2 minutes, we'll revise what we went through for the asynchronous blocking, because as we saw, blocking send receives are a bit problematic because you have to take care not to allow them to get stuck anywhere by yourself. I send I receive is more flexible. You can send, receive, and just it'll wait for the thing to complete and give you a confirmation at this wait all thing. Okay, so these are the main ingredients. The three steps are basically this in a MPI communication process. So you have your send, I send, I receive, and wait on. Okay. So this was only for one variable. If we have to do it for multiple variables, we have to put a number 10 and we have to give an array here instead of a scalar. So this will, if we were sending an array of variables, for example, if instead of local sum, we were sending an array double of p, some 10 variables. Okay. So 1, 2, 3, something. Then we would send this p and write 10 here because we're sending 10 of type double. And then we are going to receive it in an array of size 10. So we will have something like this. Initialize this just in case. And we'll put 10. So we are receiving 10. We expect to receive 10. And this will signal the actual completion of the send receive process. And whatever you have received, you can start using it here. So basically, I can only start properly, or I'm guaranteed to get correct data inside this array, which I was receiving in only after this wait all finishes. Because if I start using this array variables before this, there's no guarantee that the send or receive is completed by then. Only after wait all will it guarantee you that yes, all the send and receive requests have been completed. So this is all fine if one thing is, you'll see that in many cases, the array sizes that you have in each process are not a fixed number, which you know beforehand. Huh? So suppose you are doing molecular dynamics, where each process has different number of particles, an array of sizes, different sizes of arrays. You have representing different particle lists. Then this number of how many particle properties or how many particles you're going to send from one process to another while the particles are moving across processes. This will be some nx number, something which you don't know at compile time, so you can't hard code it here. And similarly, since we know that these numbers are going to be local to each process, if nx here in process, suppose so, process 1 is 10, there is no way of for this process 0 to know beforehand that it is going to be 10. That number 10 has to be first communicated, and only once the number 10 has been communicated, then only you can actually send the array of data of size 10. So basically, then sending arrays or arbitrary size becomes a two-layer process where first you do a send of the metadata itself. So here you will send my size or size in process 1 will be some 10 or something. This will come from some calculation in the process. It might some in Excel or something it will be. And then you have to send one data of size 1 type, this size 1 data you have to send. It will most probably MPIs inter, unsigned, long, and all those things. And here you'll receive that one data, metadata, where it will be P1 size, okay, process 1 size, and so on. And then you will actually use that size here. So process 1 will be sending its size wala array here. So this will become size 1. If it's not a constant, you have to make it a new kind of, that new delete kind of thing. And here you'll be doing a receive in some of that thing only, only with your P1 size variable that you received. So it is going to be a two-step process. So as you can see, MPI code can become ugly very quickly. Okay. A, because it is a C library, it doesn't have nice object-oriented class structures and so on. And as I said, the people who tried to write a C++ wrapper on top of MPI C libraries, it's such a bad job and such a like unhelpful job, it was deprecated. So what to do? Now, usually if you go to big national labs and all those things who use MPI heavily, you will see everyone has their own version of a favorite MPI wrapper, where they have catered to the particular functions that they commonly use, and they have written nice MPI classes and templated functions and classes and all those for using MPI. So we will start using SSLABS MPI library, which are basically the same MPI-C functions wrapped in a more user-friendly way. For example, just to transfer a vector, you can just do MPI send of vector 1 to vector 2 from rank 1 to rank 2. That's it. No all these multiple line stuff and so on. Just one line will be sufficient. So it makes the program nicer. You can focus on the actual physics, not the coding part. So all these will become much nicer. You don't have to keep track of the data types yourself. It will infer directly from the variables that you're sending in the arguments and so on. So let's quickly do one thing, and that will be a good introduction to the SSLabs code library. SSLabs code library is usually used for generating meshes and grids and things like that, and used for geometry purposes.
Sir, I had one doubt. Actually, I don't know how to use OpenFOAM, but I have heard that it has its own MPI built library. So for writing codes in OpenFOAM, we have to put this pragmas and all this of MPI code inside it, or it is automatically embedded in the software.
I have no idea about OpenFOAM. Anyone who knows OpenFOAM, can you just comment on this?
Okay. But we don't need to explicitly code using MPI, no? Acha. Oh, okay. Okay, sir, got it. Thank you.
Okay, so so now that you know a bit of MPI, like the internals of how ugly C MPI library is, let's just try to figure out how we use MPI to parallelize a actual physics code, which is based on a grid. So again, this is known to most people. I'm just saying it for a brief introduction to parallelization of physics codes. Okay. So you suppose you have a domain like this, a grid. The simplest way to decompose, like parallelize any simulation on this domain is to break the big domain into small chunks. So you'll have something like this, and let me color it differently. So okay, and I'll keep a bit of okay, fine. Huh. So we'll make it like this. So these will be there won't be any gap per se between the different domains, but these will be the slabs that you have. So suppose you have a domain decomposition like this. So you have 4 chunks. You'll if you have 4 processes, you'll break it up into 4 chunks, and then you will ask each process to update its own chunk. So for example, if I go back to the thermal, this solver library that we were writing, just 1 minute, just 1 minute. Yeah. So if we go back to the solver thing that we were writing, we can see that the main part of the code was this. Okay, the initialization was also like this. So initialization, as you can see, you can imagine how trivial it will be. What you will do is, this is your entire domain. So now instead of going over 0 to nx in the x direction, you will go only to nx by 4 for the first part, right? Because this will be 0 to nx by 4. This will still be 0 to ny. In that case, it was nx only, that's why it's nx here. But it will go from 0 to ny and 0 to nx by 4. Then for this other process, you will write it like 0 to, no, sorry, nx by 4 to nx by 2. So 2 into nx by 4 and so on. So each size is nx by 4. So in multiples of that, you keep decomposing. So after that, for the initialization part, you don't need any communication because there's nothing to communicate per se. So let's quickly finish that off. How do you make it MPI compliant? So what we'll do is we'll make a separate MPI version of this because I don't want to break the other test cases. I want to quickly get over this because anyway, we are not going to write explicit MPI code when we are going to start using the code library. All those are taken care of internally. So I would say init MPI version. Or in C++, you can usually overload functions. With if they have different arguments, you can name the function the same. So init MPI, and I'll call this MPI. So the only thing that you have to pass technically is the metadata of MPI, which is contained in MPI com. That itself will give you all the details about how the MPI processes are and how they're arranged across different, well, how the processes are, how many processes are there, and what is the ID of the process which is running this particular section of the code. Or yeah. So here you will essentially put MPI rank into +1 into. And this one will be MPI rank into. Does this make sense? Because for rank 0, you'll start from 0 and end at nx by 4 minus 1. And for then rank 1, you'll start at nx by 4 and end at nx by 2 minus 1, and so on. Okay. Again, you have to just ensure that if you really want to do it a load balanced way, that none of the, like all these are integer all these are sort of equal size, then just ensure that nx is a multiple of 4. So it's nicely divisible. Otherwise, essentially one domain in the end will start becoming a bit smaller and it will look bad. Or basically this processor will have less tasks to do. So it'll always keep finishing the tasks faster and keep waiting while these are overloaded. So it's not load balanced in that sense. So if you want a nice program which is load balanced and runs at the optimal minimal time, it's best to distribute the tasks or the load equally across all cores so that all of them finish at almost the same time. So, and similarly for this one also, we will, so this one is a bit more tricky. Actually, let's do this. So, it's not that tricky also. So MPI rank do nx by 4. And well, it is a bit tricky because technically this, we were dividing this in the whole thing into 4 parts here. Well, if you really want to write it nicely, you shouldn't hard code 4 just because I'm showing a diagram as 4. You should call that MPI rank and MPI size functions. That's your metadata, the communicator. MPI rank you'll get, MPI size you will get. Now you pass this. So now we were dividing this nx points across MPI size, number of processes. But here we'll have to divide. So we are starting from 1. Usually for the big full domain case, we are starting from 1 and ending at nx minus 2. So essentially there are nx minus 2 points total. So our per block or per process division here would be roughly nx minus 2 by MPI size. Right? And it will start from 1. So that way we will do MPI rank into nx minus 2 by MPI size, and similar here. So this will be rank plus 1 I'm making a small mistake here. What is it? Anyway, the exact bounds you can calculate yourself, like what, how it will align and so on. That shouldn't be much of a problem. So this might not be the exact thing, but yeah, like if it is MPI size, then it will end up in how bigly? This will be MPI size and nx minus 2 plus 1 you have to add because yeah, offsetting from here. Okay. So roughly this is how you domain decompose. Huh? So this part is clear, right? How you broke this into chunks, and you not necessarily break into only the x-axis. You can break in multiple dimensions. So you can even break the y-axis if you have, suppose 4 into 2, 8 processes. So each process gets a chunk like this. So these are the different decomposition methods or styles that people prefer. It depends on the problem, which is going to give you lesser surface area and so on. It's depending on what you're trying to minimize. So your domain will be something like this. Now, what we will do is we will go to this part where you have a dependency on neighbors as well. So there was no dependency, like if we are operating this point, it doesn't require value of this point or this point and so on. It's only concerned about its own point. So it's easier to domain decompose. Now, when you start domain decomposing these kind of kernels where, let's isolate one particular line a bit, it will be a bit easier. So this is fine. And, sorry. So as you can see, we have dependencies in both X and Y direction. Usually the pluses come in front if you're trying to break the code, but okay, fine. I'll rewrite it again. What about the cases where your X is such that it is lying exactly on the border of a block? Huh? So suppose I'm on this block, or this process, or this subgrid or subdomain, or whatever you call it. Usually people call it a block. If you're lying here, then the point X at the corner will require the, so let's color it nicely. So if my X is suppose lying here, this is the X point, then X minus 1 will need the value from this side block, which will happen to be on a different process or even a different node altogether. So you can't even just go and use this kind of X minus 1. It will just say segmentation fault because that X minus 1 doesn't exist for it. Okay. So what do you do? So you have to basically communicate the value of X minus 1 from this process to this process, if you need to do this step. So just before this step, you usually communicate so you will write something like this. Just before applying this step, for this particular process, I will try to receive, or I receive, as a safer version as we learned. I will try to I receive into some temporary variable. We usually call it halo or host points or padding points. Some temporary buffer. So basically, let's write it like this, some receive buffer. I will take in how many points, how many ever number of points are there on the borders, because for X minus 1, I will require all the negative X directions to get their neighboring copies. So there will be how many? NY such points, right? For the X plus 1 direction, I will need, again, NY such points to be the neighbors, NY neighbors here, to be copied into the buffer here. Similarly, NX direction, NX points for the Y plus and Y minus directions. So for copy, what do you say? NY neighbors for my minus X phase. Okay, so this phase, I will be copying into my buffer. So let's call the buffer also for negative X. I will be copying how many? So usually it is the number of points that you're going to copy, which is NY. In this case, so in this case, it is, okay, let's write it as NY. I'm not going to compile this code right now, as we'll shift to NY number of points. And then you have to say what is the type and all those, so MPI double, and where are you going to copy it from? So if this is my process P, then how do I know which process has this? That is a tricky business. Okay, so that you have to decide beforehand. If my process ID is P, which block of this entire domain should go there? So there are multiple ways of allocating processes, allocating blocks to processes. So if I have 8 processes like this, some people might start allocating blocks in this manner. So, sorry. Just do one thing. This is a bit bright. It will screw up all the views. So let me just make it a little lighter. So now, some people might want the indexing of processes. So core 0 gets block number 0, 0. Core 1 gets block number 1, 0, and so on. So if you really want to write it, give these things a label. This is block 0, 0. This is block 1, 0. This is block 2, 0, and so on. And this is block 0, 1. So some people would want just the flat index indexing. So the flat index of this would be 0 plus whatever nx into 0, right? So it is 0 essentially. nx being 4 and ny being 2 here, or ny not in that sense. This is the number of blocks. So bx and by. Okay. So this would be 0 plus bx, which is in this case 4, number of blocks in x direction. So this is 0. So if this is the flat index, so my flat index of the block is this, or flat index meaning basically, or the flat index of the block, you can say bi, block flat index, okay, or bidx or something. And then bidx 0, you say goes to core 0, okay, or MPI rank 0, gets this. Similarly, this is the bidx of this would be, if you can quickly calculate, it's 1 plus bx into 0, which basically means bidx is 1. And this goes to rank 1. Okay. And just to show another case for this one, this is 0 plus bx into 1. Here bx is 4, so this will become 4. bidx is 4 for this block. The block index is 4. So I will send it to rank 4. Other people might want to decompose in vertical way. So bidx 0 goes to rank 0, but bidx 4 goes to rank 1. And then this is like it goes in a zigzag way like this. So like this, and then like this, and then like this, and so on. Okay, there are multiple ways of doing it. And again, it's not like this one way is stupider than the other. It all depends on the problem. And later on, I won't cover load balancing and space filling curve based load balancers, which lead to clustering of local blocks in that. You can search for these huge frameworks called Metis or Aramex, which try to keep blocks which are spatially close by in the actual spatial domain on the same logical processor. Okay. Otherwise, if you randomly distribute, okay, some people do that also. The naivest way of distributing blocks is random. That is also fine. As long as it's a load balance, it will give you performance. But the only thing is, if you're going to do MPI communication between these kind of neighbors, it is always good to minimize the communication. And how do you minimize the communication of neighbors? You minimize the surface area compared to the bulk area, that bulk volume that you have. So n6n square, 4n square versus 4n versus n square for a 2D case, surface versus bulk cubes, 6n square versus n cube for 3D. So that is how you choose your block size, and then you decide how you're going to place blocks clustered nearby, so that if neighboring blocks are in the same process, the communication will be faster because it won't have to go through the interconnect InfiniBand to another node machine somewhere. It will just happen RAM to RAM, like copy in, copy out, even if you use MPI. So that will be faster. So if all these 4 blocks belong to the same node, so if I just do them a bit like sign, if all these 4 blocks belong to the same node, then essentially all their communication between these surfaces will happen within the same node. Although you're using MPI send receive, it will happen at the hardware level using just a RAM to RAM copy. It won't go out through the network, Ethernet or InfiniBand interconnect and go to another machine or your laptop or something. On the other hand, if these 2 blocks are on separate nodes or separate machines, then the communication I send, I receive between these interfaces will go through the Ethernet connection or your internet connection and all those things. And that will be slower than a RAM to RAM simple copy paste. Okay. So that is how you cluster blocks. But again, if you're using the core library, that will be done for you locally, automatically. You don't have to bother about all those things. So this is the idea of breaking a huge domain into small blocks, and how you can choose to differently allocate blocks as per to different ranks. So now let's get back to this communication business. So we were saying that we are at this point and we are trying to get the neighboring data. For this point, we're getting the neighboring data from this block into a temporary buffer so that it can be used by these kernels. So, and I'll be getting it from a rank again. So now that I have pre-chosen the rule somewhere, like before I'm calling this update, I have already stored somewhere that block BIDX, or you can say rank of an array where you say BIDX and you give the rank number. You can store a value like this. Huh. So, or you can do it by a formula. So the simplest formula based way to do it is BIDX is covered by the same rank number. So rank equals BIDX. So that way you know that if I am at some block 2 comma 0, then my left side block will be 1 comma 0. What is 1 comma 0's BIDX? It is 1. Therefore, by formula, I'll be getting that value in rank number 1 itself. I'll be asking for that value on this face from rank number 1. So it's easier if you do it by formula, but you can, if you're doing it by any other decomposition method, you just have to maintain a list of which block goes to where, which process. So that is how you copy the values here. And then these neighboring padding values are right now in this buffer. They are not in this array temp. So then there is one more step which you do where from the buffer region, or one thing you can do is you can put an if condition that if my x is the border case, so I'll put a case like this. If my x is greater than 0 locally, like if this is the 0, 0 local coordinate of this block, so local coordinate, by that I mean, okay, let me just draw the point. This is the, suppose this is the origin coordinate, just a little lower, but suppose this was the 0, 0 local coordinate of this block. This being the n4 by nx by 4, nx by 4 kind of coordinate. Then if my x is greater than 0, it means I'm away from the x minus x phase. Only then I can use this this part of the formula. Otherwise, I have to use something like, otherwise I have to replace that part of the formula with the, I have to call it from this negative x phase buffer. And the indexing will be a bit different. You have to back calculate what is the value in the buffer, linear buffer of this particular neighbor, x minus 1 point. So as you can see, all these copy pasting behavior or just copying a simple array of grid points from this phase to this processor and then using it in this step is becoming very complicated. You have to write a lot of if-else conditions, do a lot of IC, Vicent, and so on. So when we started developing our own codes, we saw a lot of these patterns repeating very regularly across all different fluid dynamics codes, heat solver codes, and whatever other codes we were trying to write, particle codes, and so on. So that's why the first idea came that we should have a unified library where all these grid data structures and underlying common MPI patterns of copy paste and all these, they get taken care of. Load balancing, domain decomposition, they are taken care of automatically so that people don't have to bother about all this domain decomposition and all those things. They can just focus on writing the physics, like the update part, the actual solver equations like these ones. So that brings us to the core library. Before that, any questions about this domain decomposition part? Any? It's fine. Okay, it's fine.
Shramadip, Shramadip.
Yeah.
Yeah, I can how to say. So the array I am declaring, I can always declare the array locally for the processors, right? Right.
Which one? This one, this temp.
So the array, the temp new, I think the array is a global array, right? So
Yes,
it is
yes.
taking global index and y. So what I can always do, I have a local array, right? And then do communication in between. And then I apply all the operators, like whatever gradient operators that will require this kind of index.
Yes. Yes, you're right. Yeah. So what he's saying is, so as you can see right now, yeah, that is true. That is how ideally it is done. Yes. That is how SSLABS, this code library also does it. This was actually a mistake. I forgot to change the local variables. So what Mohan is saying is that currently here you can see you are going from x1 to nx, which is which are basically the coordinates of the entire domain. Huh? But as we were talking before, if you can try to index points in this block local to this block, so you can choose the bottom left point to be 0, 0. The global 0, 0 would be here at the bottom left of this thing. Huh? But for this block, the local 0, 0 would be here. And if you want to just iterate over this block, because your process just knows about this block, it doesn't know anything about these blocks unless you're doing an explicit MPI send receive into buffers like this. Then basically you can just write your code where you're iterating over a local coordinate. So instead of x here, you write 0, or instead of instead of x here, you write 0, or okay, if this was, let's not do it here. Let's go to this one, the global one. Instead of doing all this business, no, you can just write, this is actually much simpler, and that is exactly how it should be done. You just write MPIs. And similarly here, ny by MPI size, or whichever way you're decomposing, MPI size x and y, if you decompose in both directions. So then your indexing becomes much simpler. And you don't have to back calculate between global, because technically unless you need to calculate global inertia moments and all those things, you don't need global coordinates per se. Or unless you're actually trying to take a CAD geometry and discretize it onto a local grid point and so on, then only these kind of global to local and local to global coordinate transformations come into picture. Otherwise, most scalable algorithms are usually written in local coordinates for blocks. So that's a good point. Thanks. This is going to be crucial in the core library. Yeah. So is this clear for people who have not done domain decomposition before? If there are any people like that, I think most people have done. Is it clear, like the basics? Because if this is clear, then the core library discussion will be very easy. Otherwise, it will become like, why is there a library at all for all this jargon? Okay. So, okay, I won't save this.
Some of the idea is that you copy NMAS, like you don't copy a particular value from the other side, right?
Yes. So the thing, so the idea is, if I need the value for this point, it's not like when I reach in this iteration for, like, I won't do the copy inside the loop. Only for this. Means, well, theoretically, yes, you can do it, but it will be very, very slow because as we learned, I did not learn this per se, but usually if you measure the bandwidth that you get on your internet, or if you're in a LAN cable network inside office or college, the gigabit per second that you get on a LAN network on Ethernet, or even on an InfiniBand interconnect. InfiniBands are basically high-speed Ethernet connections, okay, which try to transfer data faster. But they're more costly, that's why they're not commonly used across long distances also. Okay. That's why if you try to do this send receive at every iteration of the grid point, it will do a lot of small bursts of slow communication, which will slow down your code very much. Instead, Ethernet, these communications are usually done where you take a big chunk of data and you initialize this communication, and then it will slowly take your data in after some latency time and so on. And then after that, you can reuse your data. Otherwise, you can do fancy things where you know that, okay, in the next iteration, I'll require some data. You can pre-fetch it here and use the previous iteration's fetch to do a computation simultaneously and so on. So
yeah, that happens in boundary conditions a lot, like when applying a boundary condition. You need data from the previous.
Yeah. So I think, so basically, this fetch is done outside the iteration of the xy. It is done n mass, that's why this ny will be a big number, not just one. And we'll come to this in a much better, cleaner syntax inside the code library. So let's quickly jump into code. If there are no more questions, are there any questions about this part? If not, then we'll quickly jump into code. We'll just remove all this because this is bad syntax. Or bad means these are ugly syntax. Let's not keep a trace of them. So let's try to rewrite the same code using the code library. Okay. Code library, if you don't know, is present if you just search for code, SSLABS, HPC. sim core. This is a library. Okay. So you can either clone from here, it's open. But if you really don't want to go into the messy details of how it is written and so on, there are packaged versions which with version numbers which you as end users can download and use. There are different this thing also different compilations of with different compilers and so on. We'll just use the latest one. Sorry, this was not supposed to be.
So by the way, how long it took for making this library? I mean, building this library from scratch.
Let's see. Good question. No, see, the thing is, it's not done. Like it's whatever features people want, it keeps going. I think we started it in 2019 sometime.
Okay.
It's still going on, as you can see. 13th July was the latest update. So the libraries never stop getting developed.
Okay.
Okay. So instead of doing this via GUI, what you can do is you can take the URL of this. So this is, I'm particularly saying for clusters where you can't go to a browser and click and so on. So you can do a wget of the URL. So you have it. I'm using the latest version because that has the latest features, obviously. And if you want the older version, so it depends on which state of development. As you can see, all the versions have been updated because I had to, during this rejig of our local hardware, I had to transfer all the things back and forth. That's why all the dates got updated here to 13th July. But I think the 0.1.0 was released in August of 2019, something like that. Yeah. There was actually a 0.0.0, which was closed, like alpha demo, which is not talked about anymore. It's not talked about. So you unzip it, and inside this package, you'll see there are examples. There's an include, and there's a lib, and there's a license. License is nothing. Just don't share it without permission. Yeah, that's actually important. Don't share this among your friends outside and so on, because it's not worth it. So the best thing to do is go through the examples. Now, before we go to the examples are more catered towards CAD because apart from grids, the only other big major functionality that this library does is CAD pre-processing. So we will try to do it from scratch ourselves. We will try to create, like we have this thermal solver written in 2D, we'll try to create a 2D thermal solvers by ourselves. Or 3D thermal solver as you wish, because many of the functions, since we mostly do 3D simulations, many of the functions are specialized to 3D only right now. So, STL, for example, STL to marker and all those CAD functions are almost exclusively 3D because there are many small internal functions which are only valid for 3D. I have not got the time to generalize it to 2D and 1D and all those things. Yes, it can be, I just didn't have time. So let's create an example. Don't write it inside SSLABS code. That will basically screw up your download version itself. Let's write it here. Let's see. So we will say this is our, what do you say? This is our app version 2.2. Well, let's modify app only. Why are we shy about using Git version? So the first thing you'll see is NX. So okay, let's keep NX. This is fine. And we are doing hello from something. Okay, this you know now. It prints the function binary name. Dynamic arrays. So here, as you can see, you can do this kind of dynamic array thing. But the moment you do this kind of thing, you have to define your own indexing function, which we defined in. We included in this index.hpp, like declared it in index.hpp and then defined it in src index.cpp. Like this, there are many other functions which you will have to keep defining separately for no reason at all. Like for example, if you want the local coordinate for a given global coordinate, if you want the maximum, if you want the coordinate of the maximum point of this thing in real coordinates. Suppose this grid the origin of this grid in real coordinates is at -1.7 millimeter, 2.8 millimeter. Then you have to do a real coordinate to integer coordinate transformation, because obviously your array indices won't understand minus 1.5 and all those things. So you have to map those between real coordinates and integer coordinates, all those things. So all this together, the core library gives you in a nice wrapped up way. If you want to create a grid, yeah.
Hey, Samini, your voice breaks in between.
Oh, it breaks down. So I should region. Let's see. Yes, you're right. Let's drop a bit. Hello.
Hello, hello.
Now it's dropping. Yeah, now it's fine, no? Yeah. Okay. So what I was saying was, the although you can define your own arrays like this and so on, but for accessing the arrays properly, you have to define a lot of helper functions, like as I said, indexing. Like what is the flat index of a point like 1, 1, x? Huh? Then what is the, given a global coordinate, a global real coordinate, what is the corresponding integer coordinate? Because if your global coordinates are in the terms of, minus 1.5, 2.8 millimeter and so on, your integer arrays won't, your array indexing won't understand those real numbers. You have to convert it to integer coordinates like 1, 1, 2, 2 and so on. Then global coordinates to local coordinates, as we were discussing again. If you want to, you have the global coordinate of some point, you want to see which process and which point in that process's block does it belong to. Then you have to do the transformation. So all these kind of small functions are packed into a nice class for you. And therefore, if you want to declare any kind of grid or any kind of block, for example, you can just say something like, so here we will declare a single block. So we are creating a single block right now. We'll create a grid of blocks later on. So in the core library, what you do is, so what we'll do is we'll forget about all this index.hpp. We will modify solver.hpp to use SSLABS core. So essentially, we will be replacing the usage of this.
Somadev, so
Yeah.
in this context, block means array.
Yeah, so block, I'll just write down what a block looks like, then it will become clearer how it looks like. So you can call it, okay, what is the value of the, what is the value at each grid point? Because we would like to distinguish between different types of block based on the kind of object that is residing at each grid point of the block. So if you have a scalar number, like just the temperature, it's a scalar block. If there is a vector, multi-component vector or multi-element vector at each point of the block, it's a vector block. And if it is a matrix setting at each point, or a tensor sitting at each point, then you'll have a matrix block or a tensor block. There's no tensor block right now because there was no use for it at that time. Well, there is a rank 2 tensor, which is basically a matrix. But yeah. So let's create a scalar block because we are doing temperature, only one variable at each grid point. Scalar block. You have to, this is namespaced. So like you see, it is std semicolon, chrono, semicolon, and so on. Like std, the namespace under which all these functions from the core library are, it's SSLABS. Okay. If you really don't want to write such a big thing, you can simply in your codes do using namespace SSLABS at the top. Then all functions will be exposed to you. This is more like if you have written Python, it's like import something from something. Here it would be equivalent to in Python, it will be import star from SSLABS. Okay. In C++ 20, this is going to be the new syntax of modules.
Yeah, you're saying that. Is it in now?
God knows. CPU's proposals keep getting delayed. So, oh, hi, Marty. We are going to catch you about advection collision of multigrids. Like, take a course on that.
Hi. Check it.
Okay. Yeah, check it.
The master.
So scalar block, okay, what is this? How does it look like? Currently, I'm very sorry that the documentation sucks a bit, but you can have a rudimentary look by, I will try to update it as quickly as possible. I'm just not getting time to update it. So you can just search for scalar block. and see what the function looks like. So this is the hierarchy. You can see what are the member functions, and the constructors are scalar blocks. So scalar blocks takes num as a first argument, then it takes numpad, then it takes num replicas and resolution, then rmin and block flag. Okay, so what are all these random things? Essentially, what it means is, okay, by the way, you can see I opened something like a script. So everyone is familiar with template programming, right? I don't have to go into that. Or, okay, basically it means, I think you are, because see, as you can see, we have used a template here also. So basically it, the internal representation of the real numbers or real variables in your block can either be float or double and so on. So here you just say which one it is. So for example, if my scalar value is going to be of type double, then I will say it's of type double here. So it's a scalar block where the scalar number is of type double. And you have to give the dimension of the block. It can be 1D, 2D, 3D, 4D, ND, 11 dimension if you're doing string theory and all those things. You can, right now we'll start, so it's a 3D. Okay. So 3 special dimensions. And now you'll create the block. So let me call the block what? Temp. So I'm trying to, okay, let's mimic it exactly. We'll do it in 2D first, huh? So that we get the exact answers. Now, the first argument, as you can see, is num. Num basically means number of points in the block. As you might have noticed that when we declared an array with nx by nx points, we were iterating over all points for the boundary condition case, and then iterating only over the bulk points, which are 1, 1 offset from each side. So basically, the left side 1 layer, bottom 1 layer, top 1 layer, inside a block was essentially a host region. Okay. So basically, that buffer I was talking about, we keep some space for that buffer also, so that essentially what happens is the last real point, which is, okay, let me draw it like this. Suppose these are my actual bulk points. And this is the actual memory allocated, nx by nx, but this is the actual physical domain where we'll be doing the simulation. So what is happening in this extra thin layer? Basically, when we are doing that MPI send receive, the last physical layer, which we will use for our neighboring stencil, the data from this physical layer is copied into this layer, so that we can quickly reuse this x minus 1, x plus 1 syntax. So basically, this layer here, this thin layer here, let me color it. Okay. This thin layer here is nothing but the thin layer here. It's just a mirror image of that. So the first physical layer is the last host layer of this block. So, and this mirroring is done using the MPI send receives. Okay, that is actually all there is to it about MPI parallelization of scientific simulations. This in different formats you'll keep seeing everywhere. That's all. Yeah. So here, when we use this pillar block, this num that is given is actually the number of physical points. On top of that, you add the number of padding points, which is the second argument. So you can write something like this is a 2D grid. So we can write something like 2, 2. Sorry, not 2, 2, nx, nx minus 2 for the physical points, and we can add the 2 extra padding points like this, so that it will become total of nx by nx points in total, nx minus 2, nx minus 2 physical or bulk grid points. Now, this is not exactly a valid C++ syntax. So instead, what you can do is you can say something like curly brackets. Now, why curly brackets and all those? I'll just give you a brief overview of how array, std array or SSLABS array, these things work. So this is an array of numbers, right? So if, like the same array that you're doing here, or a static array, if you just call something like num 2 equals nx, nx. This is one way of doing things. As you can see, you might already be familiar with this kind of syntax, right? STD C++ libraries have this array thing where you can do the same declaration or instantiation of the same kind of object using, so these are equivalent syntax. Another way of writing the same thing is auto. You reduce the type by yourself and you initialize like this. This is more Python way of doing things. Like left side is just the variable, right side is all the garbage that you put inside it. All these are equivalent ways of doing the same thing. SSLABS code, you have, so the one thing is, these are just raw arrays. Huh? They have something like .fill function. So the list of functions that STD array has is nice. It's a good list in terms of a just generic array container, but they're quite limited. So they have add, front, back, begin, size, empty, and all this, fill, swap. Okay. That's it. These are good enough for a generic data container, but the most common array usage we see, small array usage or small vector usage we see in scientific simulations is for storing coordinates, like 3 component coordinates or for 3D codes, 2 component coordinates for 2D codes, or you have just a small 3 component vector like the electromagnetic field, like E0, E1, EX, EY, EZ, or the velocity field UX, UY, UZ. So you can pack it as either as like this. So my velocity will be 3, like UX, UI, UZ, or something like that, right? So these are the common uses of small arrays. But if I just have fill and swap and all those in my STD array, first of all, you don't have any functions in this standard C static array. So let's chuck that. STD array has fill. So basically what you can do is, the nice thing you can do with this is, so for example, you can say, okay, I don't like this, I have to change this. So fill 5. So all the components will become 5. Or if you want to swap this array with something else, like swap num with another array of the same type, num2, okay, like this. And you can get the underlying data and so on. Or you can do something like for loop. Okay, for loop will come later. That's it. There's nothing much else you can do. But the most common things that we usually do with small arrays in scientific simulations is, we would want something like, if you had a velocity u1 of a particle, then you would like to calculate the relative velocity, okay, where u1 minus u2, like this, where these are not variables but arrays themselves. That is why we created a SSLABS array version, where you get to do a lot of mathematical, algebraic, and min-max bound comparison to the power of all these operations. So if you have something like num is, and you want to define it in SSLABS array syntax, it will be, usually it is T coords, because T coordinates, T meaning generic type. Okay, the type can be double, the type can be int, whatever you want. Okay, now if you really want to do things quickly, you have named coordinates called R coords, which are real coordinates, I coords, which are signed integer coordinates, and U coords, which are unsigned integer coordinates. Okay, so let's do R coords because we are doing double here. Or if you want to really keep it the same way, syntax wise, let's do double. So different teams like to hard code the value of R, or they can use a T coord. So it depends on your personal taste. Okay. Usually we do R coords because unless there's a good reason, let's do double only. So R coords by definition is double. And here, what is the dimension of this, or how many components? 2. So again, you can find all of these in the search bar. So R coords, if you search for, you'll see it's here. Okay. So where did it go? R coords is basically a T coords R coord, where R coord is double. These can be listed in a nicer way with some more words explaining them. But what more will you say about this? R coord is type double. That's all. Okay. There's a better way of writing documentation actually. So R coords is like this, and what you'll do is you want to initialize it. So like this only, you can say num. By the way, num is technically int, so it's not argcods, sorry, but okay. So like this, you can do. Or if you want the other way, you can also do it just like you did with std array. This. So till here it is clear. So now these arguments, the scalar block as the first argument takes network went down, is it? Okay. It takes a quartz type. Quartz type can be anything like it can't be anything. It has to be a unsigned U quartz. If you look at quartz type, sorry, if you look at quartz type here, it's a base type quartz, and base type quartz is basically your. We'll show here. Quartz type is base type quartz, U quartz. Okay. This is so commonly used. Once you get a segment compilation error and you fix what the or understand what the type of the thing is, it will just become second nature. You don't have to remember which argument is what. Usually, all integer coordinates that we use are U chords. All real type coordinates we use are R chords. That's it. I chords are not usually used unless you want to do subtraction kind of stencil operations like x minus 1. If you use unsigned coordinates there, it is possible that if you're doing 0 minus 1, it will overflow to nuclear Gandhi. So for that reason, we just give me 1 minute. Huh? Just give me 1 minute. I'm getting a call from Nachiket. Yeah. So we have this. So usually these are num variables, which are like sizes or numbers and so on, are U chords. So we will declare a U chords. So num we will say is a U chords here. We'll delete all these intermediate things. And it's always good to, anyway, it doesn't matter if you take an int and you try to initialize a U chords, it will automatically cast it. Actually, it might not. Let's do it as U chord. You can call this unsigned long or whatever you want. Usually you have ATOL or UL for unsigned, but okay, we'll call it unsigned long. If you want unsigned U chords. Or the equivalent, the best way to do size types are std size. This is standard way. All libraries use this favorite thing. Anything that has to do with size or numbers, unsigned numbers, basically sizes only, is size t. Okay. There's a number of points, real points. Number of padding points will be 1 on each side. So 1 on each side means left side there is 1 layer, right side there is 1 layer, like this. And this basically means this whole library assumes your left side and right side padding points are equal. It's not like you have something like this. Okay, like left side you have a huge padding point and right side you have only 1 padding points, like large number of padding points and so on. So because for all practical cases we have seen, you can write a library like that where each direction has different padding points. There are hardly any physical problems where it occurs naturally. You can always cook up a fancy problem like that. But padding points can be different in the x and y directions. Like for example, x direction can have one layer, but y direction needs 2 layers. That happens when you have compressed grids or rectangular grids or something. So that's why this first component of all these num and all these small vectors represent the x component. The second one, the y component. If you had a 3-dimensional coordinate, the third component would represent the z component, and so on. So this looks fine. No? See, the idea is it should look almost like how you would write in LaTeX or a mathematical equation. Okay, instead of trying to, the goal is that we actually had a library like that where you could just write an equation format, we'll compile it into a code and so on. But that is not used currently because people hate it. So
Why?
Atif actually knows about this.
Oh,
Atif.
Atif, okay. Is he here? He's not
I
here.
don't know. I don't think so. It was called Panini at one point of time. Yeah.
Oh,
So
okay.
we had Intel had come to include it in their compiler, then the talks got derailed.
Uh,
So
maybe you should discuss about that.
that is like decoration on top. Like who will want to write a LaTeX? So that was basically for clients who really don't like coding. Like, 70 plus professors who want to just write LaTeX equations and want the code to run behind the scenes like that. Yes, as a technological feat, yes, it is doable, but what is the reason? Actually, Oracle was
I want to
developing.
hear that interesting story.
Which one?
I mean, about that, the thing that you told now.
Oh, okay.
The Panini thing.
Actually, Oracle and Sun Microsystems, not Sun Microsystems, Sun, they were trying to build a Fortran-based wrapper where you would be able to convert LaTeX equations directly into C++ HPC like codes. In 2000s, it was called Fortress or something like that, but they found a lot of problems. But then we used a lot of template programming, and we were able to basically you could write things like this. So you could write f of some field, f of x, y, z, equals sine of x into cos of y, and so on. Just this line. It will actually loop over all the, and you define what your x is, like this only, like you got. Huh? So here you can pull it into SSLABS parts, the SSLABS code. Not an issue, but okay. Our chords, suppose it's 3-dimensional, you write it as my x goes from, you have to basically tell where to where. So
Okay.
it will be like this. So x goes from 0, 0, 0 to 1.5 in real coordinates. Huh? So
they could have contacted GNU plot like that.
Yeah, and so when you write it like this, internally loop over all the XYZ coordinates, like suppose you have XYZ coordinates like this. So this will allow you to, just one line, no need for for loops and so on. Okay. So it will be just lines and lines of equations, that's all.
Okay.
Anyway, so, well, in SSLABS code, you have one line of for loop, not 3-4 lines of for loop.
Yes.
Actually, internally it uses that only. Okay, so let's get back to what is implemented. Okay, someone was saying, what is the future roadmap? Maybe this is one of the future roadmaps to integrate patterns. Okay, fine. Let's quickly finish this part. Huh? So numpad will put, if you're not doing any communication, your padding point can be 0. That depends on the physics problem that you have. There's nothing to do with SSLABS code library. Means you can put as many padding points as you want or not put. It's up to you. Then what are the arguments? Then you have numrep. This replica business, please ask your respective group managers. I'm not going to comment on this. Just take it as a default one call. So the simplest way, if you really wanted to just create a grid, this is it. Okay. Like what we had written here, this is it. The other extra optional arguments are basically if you want to now give a real coordinate up to the origin point of your grid. So for example, as I was saying, right, if this block in real coordinates is like minus 1.5 comma 2 minus 2.8, then you can pass that here. So you have to just put the replica thing by default and then pass another min, or what is called as real min. Okay. So this would be a real coordinate, r chords 2, and you give whatever you use in meters, suppose minus 1.2 comma 4.7 some meters. Then you pass armin here. This is useful if on the fly you want to quickly print in a file the data values at each grid point corresponding to their real coordinates for some reason. Or if you are calculating, suppose the moment of inertia with respect to a point here, then you need the real coordinates of each point. So if you give the real coordinates of your origin point of the block, it will automatically give you the calculate the corresponding offsets for getting the real coordinates of each other grid point also.
Okay, so basically R mean is the point where the padding points begin, and after
Okay,
that
no. So good question, good catch. R min is the minimum coordinate of the physical block.
Okay.
And we'll come to that. If you just have to give R min, it will automatically give you it will offset by the negative distance and give you R min padded, which is the real coordinates of the minimum padding point. We'll come to those. What are the internal functions? So in the argument, you give the real coordinates of the minimum physical point. That's a good catch. Thanks. Otherwise, it would have been very bad. So actually, yeah, these are like when I was coding, this was becoming a bit confusing. So you can see the signature is a bit different. First, you give resolution and then Armin. Because Armin, many people don't like to give. Resolution still is more often used. So resolution is basically the real resolution, if you want to give something like that. So suppose the distance between 2 points in my block, between any 2 points, is suppose 0.1 meters or something along all directions. So I'll give 0.1, 0.1. And if along x direction it is 0.1 and 0.2, it will be like this. So this is how you create a very generic, like fully scoped out block. Usually people don't use all these. For our purposes, we're not going to print the real coordinates. So, or do you want to see real coordinates also? Then I can keep it. Okay, let's keep it, fine. Then let's make these numbers a bit nicer so that they look, you can quickly mentally calculate if you're getting the correct values or not. So nx is this. So let's see. What can we do? We can first write a unit test to check actually it is all going through. So let's quickly go down and write a unit test. That this is actually true. So this would be a good revision of how to write unit tests also. So we will quickly copy paste or we'll start from scratch. Test, what do you say? Scalar block. So what do? You hash include your catch file. So catch.hpp. And you would need to include SSLABS, the grids folder itself, because that is where the scalar blocks and all those things are defined. So grids.h. Why such a big thing? Why not just like grid.h? Because you can have you can be including multiple libraries in your code which have a grids.h thing. That's why just to scope it out and ensure there's no conflict, you can scope out the entire path with a unique signature. Test coordinate transformations. So what we can do here is we can't pass anything from command line because tests will run automatically. So let's say std size t nx would be how much? Let's say a size 100 block. Let's say, and then we'll give it 100 this thing. So the total block size will be 102. Right? And then we will say this is our min, our max. Resolution is this. So if my resolution is 0.1, then my real block length will be how much? 10 meters, is it? So it's usually nx, nx minus 1. If you're, it's basically if you take this to be the first point and like, does everyone see why it is nx minus 1, not nx? So if this is your first point, and if this is your last point, and if you have nx such points, what is the actual distance? And the gap between each point is res, then the length of your block will be nx minus 1 into res. Because you'll only count the segments. If you multiplied nx into res instead of nx minus 1 into res, you will essentially end up having a length like this. Okay, so that is what we want to avoid. So the first thing we will want to do is...
Can you repeat the last
point?
You were breaking.
So, okay. So basically, the length of this block from this point to this point is res, which is basically this small dx or the line segment into the number of points minus 1. So if nx is the number of points, the length of this line is nx minus 1 into res, not nx into res. If you did nx into res, it would basically mean the length of this line. Which, if you wanted, you can put it like that. But usually in the code library, we define the length to be point to point. Okay, not like hanging. Oh God, this is bad. So, okay. So we have our stretch.block here. So we'll call it. This type can be anything. You can put integer variables also here. But for now, since we're doing temperature, we'll put this thing or 2. And if you don't want to keep repeating 2, you can make it also a constant here. So usually in C++11 onwards, you can use, not this. You can call it constant, std size d. Dimension d is 2. So then you can scope out everything d. That way, if you want to change dimensions, you can quickly. But then we will say but here anyway, I'm hard coding only 2 numbers. If you have repeated numbers, SSLABS core gives you a very simple way to fill in all elements with the same number, just like std array does. Fill. All the d components will be filled with number 1. Okay. Similarly here, like since this is repeated, we'll fill in. So this portion basically creates an empty object, right? Empty constructor, where all the initializations are sort of undefined or null or something. Then you initialize them with fill. Or you can write it out this way if you want there to be a difference. In this case, we want a minus and plus just to see whether subtraction and addition is working fine. So we'll keep it separate here. So we have this, or some people even want to scope out this template double type also. Usually you'll see people writing something like using t. So in C++ or in C, you will be doing something like type def double is t, right? The nicer equal to way in C++ 11 is t equals double. Same thing. So you can replace this with t. That way you don't have too many, hard-coded signatures floating around here and there, no duplication. That way you can just change at one point and everything will get changed. So that's nice, cleaner code, less buggy it will be. Okay. So you can create a block temp and pass in the arguments numpad, res, and armin. Okay. Now to see if the internal quantities are coming out fine or not, what you can do is you can say that I want to check for some usual quantities. What are the usual quantities that are available? One is to see if things have been set properly or not. So you can say, show me what num value do you think I gave you? Okay, like this, you can say. And if you do that, then essentially it will give you, okay, let's quickly, what we'll do? We will first make this int main function so that we can just show you the printouts first, then we'll convert this into a test case. So that is how you usually write test cases. First you run it yourself once, and then later on you remove this main and make it a test case. So I'll put it IOStream because I'm going to print it now. And then, yeah, that's it. And see if you're getting back 100, 100. So what we'll do is we'll do G++ test scalar block. And to link up the SSLABS code, you have to include the signature, the header files. So, sorry, there's a chain going near my house. And include. And you link the library which is in lib. So what is there? So you can go to desk, whichever the location is. You can also use a nicer, cleaner CMake syntax, but right now I'm just showing you the raw way of doing it. Huh? And see, there are multiple things. One is lib SSLABS core cat.a, this thing also on. So right now I'll be using only grids functions. I'm not using CAD yet, so I'll just include SSLABS core grids. Sorry, it needs MPI also. I am going to make a MPI less version, but by default, everything right now, everything. Actually, you can remove MPI usage by defining, by compiling with minus no use MPI, but it's best not to do that because most of your functions internally are calling MPI somewhere mostly. But anyway, I'll release a non-MPI version also. It takes a bit of refactoring. Whenever I get time, I'll do it. So usually the sequence is your own libraries, third-party libraries, C libraries. Oh, this is because I am calling an MPI code using a G++ compiler, which is not correct. MPI C++. And this is currently compiled using mpitch, so I'm going to use mpitch. Sorry. Oh. This is going to be a bit of a problem, but okay, fine.
Oh, MPI C++ or MPI ICPC is better, man?
Ulta, no? Samiti.
Huh?
MPIC.MPIC++, right?
Oh, is it like that? Oh, yeah, I keep forgetting. So yeah, obviously Intel would be better, but till now, actually, we didn't have the free Intel releases for the compilers. So that's why when I was releasing the generic version, it was using. So I released the latest version, which is generic. It is compiled using GCC and mpitch. There is a proprietary version which is compiled on Rudra, GCC plus Intel. And there is a single legacy version that is for them and so on. So right now I'll release another build, which is like, so if everyone is using Intel compiler, everyone downloads Intel compiler on all their machines. All the machines, the shared machines and Rudra has Intel compiler. So if everywhere you have the free Intel compiler, then I'll release only the Intel compiler version. Then I will remove GCC altogether. Okay. So that happened as a recent event. So that's why I'm just, yeah.
Or in this case, we can I was just thinking, in this case, when on the cluster you have installed something and all, and we have to run on local machine, we can use Docker, no? Like we can still create the image there, just run it here. Is that possible?
But why do you want to log into Docker, compile there, then again get it back to your laptop?
Because again, you don't have to install on yours. Like again, you.
If you're doing a test, yes, that's fine. If you're going to do a production run, it's best not to run it on Docker. Yeah. Because Docker will slow. It's like a middleware, no? So it will slow your. For a test runs, yes, you can do that. Actually, Maruti, you also used to do it, no? First one.
Yeah.
Yeah, means if you don't have your local environment installed that way, yes, you can use Docker for testing purposes. Yeah, that's completely fine. Yeah. Okay, all these, there are a few things. So, or should I just go into Rudra and compile because that is a clean environment?
Yeah.
Just doing it with me. Huh?
Rudra is better.
This version. Okay, fine. Let me just try to quickly. mpitch does. Okay, let's compile with OpenMP. Don't do this because I don't have currently mpitch installed. I reinstalled my laptop OS. That's why it's not there yet. Or I think it will be there. Wait. See. Error is it says scalar block is not declared. So it says please put SSLABS this thing. So I thought I put it, no?
It's not test.
Okay. So using either you can put namespace or you can directly. Hey, I put everything. Oh, it's only one thing. Yeah, you can scope it, or you can put using this. Let's scope it because then it will be clear what is SSLABS function, what is not. So we compile. Oh, what is happening? Oh, syntax error. It says numpad. Oh, since I was trying to so badly avoid replicas, replica is something again I will not explain. So this compiles and now we'll run it. This is 100 by 100. Nicely it prints. Okay. It's good. It's checking what we wanted it to. I will not explain replica because I expect you to go and ask your respective managers what replica means. This is one task you should have.
I think Chakri told us that day, no, Maru? It's like
Yeah, no,
the
this
hierarchy structure, basically. Like you use the same thing, but I mean, that's what he said.
Is BCC.
Correct, but it's a hierarchy in your grid, no? It's the same thing, but
Don't
you're using
replicate
one
it.
more layer.
Yeah.
I don't know.
Ah.
Like that's what I understood it as, and yeah, probably I should read.
So okay, a BCC grid, as you would know, is basically a okay, fine. There is a whole slide on this, I think, somewhere in my folder, but I'll just quickly tell how do you quickly show something like this.
See, Somadeep, we should have told to ask Ansu rather than managers.
Ansu will not talk to you.
Yeah.
If you ask these kind of questions now, he won't talk to you. So, okay. So I'm trying to quickly make a grid. And I'm doing a very slow job at it, but okay. Fine. No. Okay, as you can see, it's a grid of some sort. Okay, so that is fine. So this is a SC grid or 2D SC grid, as you can see, square grid. In two-dimensional, the equivalent of a BCC grid will be something where you put, so these are the grid points, by the way. Grid points are here. So you can imagine grid points here, 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 and so on. It's not going to be aligned, but okay. These are the grid points at each place. A BCC grid is one where you have also extra grid points in the middle, body center. In 2D, it looks like this. In 3D, it will look something like, body center. Like this, it will look. So if you have something like this, then a body centered grid, you can just connect the offset points or the body centered points by themselves. And then you will see that you end up having, creating a sort of SC grid by of itself. Okay. So all these will be connected like this. And so on. Now there are multiple, so basically if you want to really replicate it then and see that it is actually making a SC grid, you can just do something like and these will be connected to each other and so on. Let's connect these other points also. So you can see that it itself is making a SC grid. So essentially a BCC grid is two SC grids offset from each other by dx by 2. That is one way of representing it. There are other ways of representing it. You can unravel it into an alternating square lattice itself with alternate edges connected or disconnected and so on. Okay, like this you can create a BCC grid. So basically replica basically means that now you can think of an FCC grid also. An FCC grid also you can represent as, I think, 6 clones of an SC grid. So replica, that number basically means how many replicas of the SC grid are there. If it is 1, it is a simple SC grid. If it is 2, it's a BCC grid. If it's 6, it is FCC. We don't usually use FCC, so don't try to put 6 in there. But it's there just for as generic purpose. Or if you have some other interpretation of using cloned grids, use that. It's not an issue. Initially, we did not hard code anything with that replica number. It was just a clone grid. But right now, since we have been trying to make the functions more smaller and user friendly, in some cases we are using this replica number to just mean SC or BCC. So there are some cases. So for example, I'll tell you, if it is properly offset like this, no, the first problem that you'll see happening is, let's see. Is technically it will be, if the whole grid is offset, it will like hang out like this, and on the top also, sorry, on the positive X and positive Y direction also. So then the R max of your grid will not be this point, it will be the point here basically. Then the R max real coordinates will also change depending on whether you have your block has a replica, a secret or a BC grid. Initially R max actually R max just means this. You are supposed to take care of the replica Rmax, like your real replicated Rmax and so on. So most functions that you use in SSLABS core library basically interpret that you are trying to call it on a simple SC grid. If you need the corresponding BCC versions like Rmax of a BCC grid, you have to multiply, you have to add a 0.5 into rest to your Rmax. Okay, we'll come to that. We'll come to all of this. So right now we are just quickly trying to verify whatever we have said, it's coming out correctly. So 100, 100, 1, 1, 0.1.1 minus 1.5, 1.5. It should come out like that. So let's see if it comes out like that. So this is fine. This comes out. I'll just quickly go through this because now that you're getting the hang of how to do things, now I'll quickly jump over what are the functions which are usually available apart from this, whatever you gave them. So Rmin, as we discussed, is just the minimum point of the real coordinates of the minimum physical points or the bulk points. If you want the host points, real coordinates, what do? You just say Rmin of the padded region. Okay. What should it be? It will just be the real coordinates of the physical region, the minimum point of the physical region, minus numpads into dx. So we have one padding point. Numpads is 1. So basically it will be minus 1.5 minus dx, which is 0.1. So it will be minus 1.6. Here on the y direction, it is 1.5. So it will be 1.5 minus 0.1, 1.4. So you expect this to be minus 1.6 and 1.4. So let's see. Correct. So now let's see Rmax. Rmax is supposed to be, as I said, the core library functions only interpret your grid as a SC grid. Although it gives you an option to store different replica grids, the extents and all those functions assume that you're asking the extents for the SC grid itself. So Rmax is supposed to be this point. What is the value of Rmax supposed to be? So, okay, before that, what is max in terms of integer coordinates? See, you have nx points, which is 100 real points. Numpad is 1. The total number of points in the entire block is then how much? Numpad plus num plus numpad. Okay, so let's just print that once. It's called, the total number of points along each axis is called numpadded. So number of points in the padded region. Usually if you have a confusion about what the syntax is, every underscore you can interpret as off. So num of padded region, basically, block. Similarly, Rmin of padded region, and so on. Otherwise, it could have as well been called a padded num or something like that. Padded of number doesn't mean anything. It's a number theory question. Okay, so number of padded region, number of points, basically. I could have called it num PTS and so on, but already people are complaining that these functions are so long. Our code doesn't fit into 80 characters per line. That's why I tried to keep it small. Okay. But if you call it numpy, then other people would have said it's too big.
But this is good now. Otherwise, at least it's not confusing. I mean, if you just keep shorter names, then
yes, exactly. Yeah. So that's why this naming, what name should be chosen, that itself took 1 week first. Like a lot of thought has gone into it, but if users don't like it, what to do? Reiteration has to be done. So people apparently don't like T chords. It sounds very nasty, like very irritating. T chords. So we'll see. Anyway, so num padded. Let's quickly print. What should it be? 102. It should be along each axis. 102 along each axis. Then what else? So basically, you can see the entire list of functions if you just go into the block and search for block. If you search for block, it won't show. So search for scalar block. Also, it won't give you much data because scalar block actually derives from this thing, from this block thing and tgrid. The main thing that is the core of this core library is the extend class. Extend class gives so many things to all these things: matrix grid, matrix block, multi-grid grid, and all these things. Extend basically doesn't store anything. Extend basically is a class which stores the metadata of any extend or any geometry property and so on. So here you can see what all properties it has. You can set numpad, numpadded, and all those things. Num, min, max. Min, max basically give you the integer min, max coordinates of the physical locations. So if I print min, max, you will see.
So is extent like a class you derive other classes from?
Yes,
like,
exactly. Yeah.
Okay.
The mother class.
Class, yeah. Okay.
But it doesn't allocate anything itself because apart from the metadata itself, there's no it can be used to define the extent of any type of grid, right? So, and the grid is actually the one which allocates data, depending on the type of component that is used, matrix or vector or scalar.
Right. Okay. So the other classes that you actually call here and all, somehow they're derived from extent.
Yeah. If extent is removed from this library, the whole library collapses. Or the grid, actually the cat part also collapses. Both the grid part and the cat part collapses. Yeah. So basically, then you have just a mushy mess of grid points, no geometry metric on it. It's like a topological problem, not a geometry problem anymore. Extent gives you the geometry structure. Otherwise, it'll just be loose connectivity, like an unstructured graph. So, min-max, then what else is there? Min padded is there. So basically, what is the minimum of the padded region? And min and max basically mean the integer coordinates. If you want the real coordinates, you have to do rmin, rmax, like we did here. So let's do min. Let's do it side by side. Integer coordinates, temp rmin. This will say is the minimum portions of the block. Again, this metadata, I'm just showing you quickly because we'll keep, for doing any kind of grid thing, access and so on, we keep using these functions only mostly. Basically, all your code will mostly be massaging of these numbers only, that's it, apart from the actual solver. Will be Rmax. We'll pay particular attention to Rmax. Let's define it as 1 first, then we'll change it to 2 and see if it changes. That will convince you whether BCC changes things or not. Otherwise, it will say what you have to include by yourself to make it a BCC thing. Length is basically the real length as we discussed, which is r nx minus 1 into res. You can print that if you want. Length is... Usually this is not required per se. And this will give you the length of only the SC section. From this point, for example, to this point, not this point. For this, you have to add a half dx extra. So usually people write, if replica equals 1, then add a plus 0 into half dx, or if replica equals 2, then add 1 into half into dx. Yeah. If replica equals 1, don't add anything. So bounding box or B box shorted gives you the real bounding box, okay, of the coordinate. So basically it will give you a box data structure which contains the rmin and rmax. So usually you can pass it to, there are algorithms where you'll need the bounding box of a grid and so on, real bounding box. Zone I'll come to replica max and all those. And there are floor ticks, seal ticks, round ticks. I'll come to these also. These basically take in a real coordinate, r coords, and give you the corresponding integer coordinates. Now, this is the interesting part. If my grid has these kind of data structure, forget about the BCC part. Right now, let's talk only about the SC parts. Suppose I have a point which I want to, I have a real point for which a real point like this somewhere here. And I want to know, I want to basically figure out which is the grid point closest to it. Now, what do you mean by closest to it? It can either be below here, above here. It can actually measure the distance and find closeness and so on. Usually distance finding and all those, if you want to do it, you can do it by basic, for basic necessities. I've just given 3 different options, which is it'll either round it below, which is the floor function, either round it over, which is the ceiling function, or round it. So basically, round basically is that if the it is sort of implementation of the distance function itself. So basically, it will try to measure, okay, in between these 2 things, or let's say, let's just put it here. And imagine I'm trying to compete between only these 2 points. If it is closer to this point, see, if it is like this, if I do float, it will come here. If it is seal, it will go here, even though it is far away from it. Round basically says, okay, which is the closer one? I'll go to that. So basically, if you do round ticks, get me the round ticks. Ticks are basically the integer coordinates, okay, and r coords are the real coordinates. So if I say that give me the round ticks, it will take me here. If the point was here, it would have taken me here, the closer one of the 2. So those are the things. And index 2D and 3D basically gives you the flat index. Okay, you usually don't use it like this. I'll show you how to use it later on separately. So basically, these are the.
Somebody, do you use that seal and that this thing converting from real to integer in STL and stuff to?
In STL, you mean from STL to marker?
Yeah. I'm just asking because there also you do 0 to 1, like either 0 either 1, no? From real coordinates.
Yes. So, well, the STL to marker algorithm is not just taking real coordinates and mapping them onto nearby integer coordinates. It is actually a very geometric algorithm where you take each triangle and see which edge of the grid is actually cutting the triangle. Then you either cut those edges or retain those edges, and then you do a clustering algorithm on top of it.
Oh, there's a lot. Okay.
Yeah.
Cool.
Okay. So otherwise, if you just do, initially we were doing that.
Correct.
It turned out to be horribly inaccurate.
The boundary would not.
Yeah, it will distort a lot if you just do seal and floor. I think in when was it, Ravi? 2018, 2017. It was being 2017. It was being done like that, just seal and floor. Yeah, it was fast, but yeah, very inaccurate.
Okay.
Then we came up with this fancy algorithm. So. Okay, so this is the min-max length, and I'm just showing you what you can play around with it. Like you can create a small function like this just to get a feel of it yourself. You can put different values and play around with it. I'll just print these values for now. Or are there any particular other values that you want to know? Then I can tell. So okay, let's guess. Why is this length 9.9? Let's go back and see if it should be 9.9. So as I said, it's nx minus 1 into reds. Nx is 99. Nx is 100. Nx minus 1 is 99. And your resolution is 0.1. So 99 into 0.1 is 9.9. So that's why its length is this. Max is whatever your min. These are the integer coordinates. So let's look at what max is. Max, it says, is the integer coordinates is 100, 100. And the real coordinates are this. It's 100, 100, not 99, 99, because the minimum physical coordinate itself is offset at 1, 1. So this is one thing you need to remember. For the core, this SSLABS core grids, the minimum padded point starts from 0, 0, and your minimum physical point starts from whatever the padding point is. So this will be 0, 0, then this will be 1, 1. The next one will be 1, 2, 2, and so on. Similarly, it will go up to your maximum physical point, and then it will go to max padded. So now let's do a loop. So this is fine till here. Any other questions regarding the basic block functions themselves? Rmin padded, Rmax padded. So as I said, this will only, Rmax will give you only the SCs max, even if it is a BCC grid. For BCC R max, you have to take into account. See, the problem is because we wanted to keep the interpretation of the replica not tied down to BCC. That's why we don't check key if R equals 2, then offset it by half and half. Because I can have a different grid like honeycomb lattice, which also might need R equals 2, R equals 3. And then I have to do a very different kind of thing. So right now, replica is treated exactly how it sounds. It's just a cloned grid of SC. That's all. So fundamentally, everything is SC. But if there is popular demand, we can decide that once and for all, we will not do simulations on any other lattice like honeycomb, T-type, FCC, nothing else. We will just stick to BCC and SC. Then we can make it hard-coded that R equals 2 means BCC. So when we call a R max on a replica 2 grid, we will give automatically internally generate the point half dx offset. So it's up to you. Let me know.
Sorry, the blocks that you create, these are cubical or they can be
no, they can be anything. Yeah.
Anything, right?
Yeah. So you can put
but
it
these are rectangular blocks. It's not like it's as in it has a min and max.
As opposed to sphere, spherical coordinates.
Something. As opposed to some polygon. And
yeah.
Okay.
But your sizes can be different, your resolutions can be different, although please don't use different resolution things because LP codes right now assume uniform resolution in both x and y, like dx equals dy. If you're going to change resolution, then talk to your manager.
And NX and NY could be different in LBAC.
Yes, NX and NY can be different. Basically, it will basically look like this. Let's see, NX and NY different means no, this was an example of NX, Y, and Y different. Dx is the same, dx equals dy, but nx is how much? 1, 2, 3, 4, 5. Ny is 1, 2, 3, 4. So there's an example of nx not equal to ny, but dx should be equal to dy as of now. Not in code, it can be different. You can put a different resolution for each axis. The solver codes will break. So please talk to your manager before you try that. So compare
somebody, and can you comment on normals to these spaces if they're there as function?
No. Where would you what kind of normals would you want?
So let's say you take one SC grid that you've drawn, which is dark black, and you take one cube there, one square or something, and you want to find fluxes or something, let's say. On these things.
Interesting.
So, normals.
Right. Yes, I understand. See, the thing is, most of these grids and functions were written keeping in mind the requirements of LB. LB till now is a point-based method, famously point-based method, and it doesn't have the use of these dual spaces. Like dual to the point will be the in 3D it will be the surface area, then dual to the edge will be and all those things. So for that we were writing a small code which had all these dual elements for using this thing called exterior differential exterior calculus. Okay, which basically is the formulation which governs FEM, FVM, and all those things. But since that is not optimized for HPC performance, we don't talk about it. But so no, the idea is, since we are mostly doing LB and not FVM and FEM and all those, there was no requirement of such a construct in the core library.
Got it.
If over time we have such a requirement, definitely we can put it in. I understand. I completely agree with what you're asking for.
Actually, Maru, can you elaborate on this, whatever I'm asking him, because you.
Yeah.
I don't know. Maru is there? Okay.
Yeah, I think he knows now. Yeah, so whatever Samiti best to.
Okay. No, that's what. Cool. Yeah. So actually, there's a requirement, Samiti, because we are discussing in that group that.
Yeah.
So you probably know.
Okay. So basically, if you have any for everyone, if you have any requirement, just go to issues, new issues, type away. I want this. See, look. Judge has
Popular
3
demand
with
control.
no, so that is the idea of issues. No, see how many issues? So many issues are created by users, and we have closed also so many.
So where would you create this on the HPC thing? Wait,
So the library name is this. Any requirement that you have, just put it.
okay.
So all these are like user issues only.
Oh yeah. Okay.
Okay, it looks in my name because I am the assigned person in these cases. But as you can see, Jaju, Milind, Rohit, all of them are created stuff.
Nice.
So please type away. Okay, we'll go back to our presentation. And okay, so this is basics of block and the functions and extent. Now you have created a block. Now what do you do with it? Okay, so let's quickly jump into, let's remove all these. Should we create them as test cases? For now, let it be. Because anyway, internally in the core library, I'm running all these unit tests, so they are bound to pass. Otherwise, they won't even release this. GitLab won't even release this package to you. So this is my, I'll keep it as 100. I can make it to 120, but just for this. How do you iterate over a 2D grid? Usually what we would do is for int x equals 0, x equals nx, x plus plus, and two spaces, no tabs, especially not for spaces. Okay. And if you're doing in 3D, it will be one more loop. Okay. Let me actually do that to make it look bad, nasty. Because that will motivate the next thing we are going to do. Or one of the nicer features of the core library. Use it wisely, it is a bit slow, but it can, for the non-performance critical portions, it will simplify your codes a lot. For this, if you have a 3D grid, you will do something like what? Okay, if you had that kind of a grid, you would do x, y, z, and so on. Or if you wrote your own index function, you would do something like I and bx, x, y, z, then nx, and y, and z, and so on, right? Like the way we were doing. You don't have to do all these things in SSLABS code. Just call it as x, y, z. That's all. Okay. Because temp already knows what your extents are. It will internally calculate the index and so on. X, y, z equals. You put whatever value you want. This temperature, no, we're doing bulk is 80 and so on. This is your way of doing it. And because these 3 lines, you have to keep looping over grid points most of the time in any grid-based simulation, this has been simplified. How? You will iterate over all x, so call it auto. X is now a vector grid point. For x in temps, or let's say the min of temp, as long as temp contains x and temp text. And here you'll just put x. Does this?
I mean, when you say it, I mean, it reduces performance a bit.
Yes,
like how much?
How much?
Yeah,
How much? No, so for basically any part in Advect or Colite, don't use this.
okay.
That's all.
Okay.
Is the syntax familiar or understandable? If not, this
Not
is
used it
generally.
before. You can just elaborate. I've not used this.
Okay, fine. So if you write a for loop, usually what you do is the for loop, C++ or C for loops go like this. This is your initial condition. This is your final condition of stopping condition, so 100. And this is your every time step increment. Is it? Technically, what it is doing is it is actually evaluating what this value is at each time step. Is it true or false? If it is true, then it will keep iterating to the next step. If it is false, then it will stop. It will exit. So technically, in this second bracket, you can just put any true false condition. Temp.contains basically checks if this x ucords, the local x coordinate of the block, is still within x even if at every iteration you are just going to x, next, x, where next, x is being done in a typewriter fashion. You start from the lowest 0, 0 or 1, 1 min point here. Temp min will be 1, 1 as you saw, if there is one padding point. You start from here, then you do your stuff, then it will call temp next.
So contains
What does this next
returns
function
a
do?
bool, huh?
It just increment. Yeah. It's
Okay.
it's like this thing in different objects of SSLABS code like box or cylinder and so on. Anything like a box contains this will tell you whether the coordinate is contained in the box or not.
Oh, nice. Okay. Cool.
So temp is okay. I'll come to that. So technically, temp is not a box. Temp is a grid. You have to generate the box of this. So BB box. Okay.
Oh, okay.
If you want to make the code less ugly, and here also it's a BB box. If you want to make the code less ugly, just call it like this. Constant auto, my zone of iteration is temp.BB box. BB box is actually a real coordinate. You want the integer coordinates. So just say get zone. Zone will basically give you the min to max. So this basically gives you temp min up to temp max. A box with this. Okay. So basically it will give you 1, 1 to 100, 100.
Okay.
So basically, it creates a virtual grid on the fly.
Okay.
One like it is basically like that reshape function that you use in MATLAB or something. Or
okay. Right.
Cool. So temp zone, and then you will just call zone here. My zone from my zones min to zones contain and zone next. How does next go? Next will basically go in a typewriter manner where you start from the min part and then increment first the x-axis. So 1, 1, then 2, 1, then 3, 1, then 4, 1, 5, 1. Then it will jump to the next axis. So then again, it will become 1, 2, 1, 2, 2, 3, 3, 2.
Okay. So basically, next will again return coordinate +1 in some sense.
It will update the x coordinate and return yes.
Return that thing. Okay.
Yeah. So like this, you'll cover your entire grid. So now basically you can do it in any dimensions you want. Okay. So this code actually will work in any dimensions because there's no dimension, it's dimension independent. Everything is done internally here. Right. So that's why you can very nicely like modify your codes from whenever string theory becomes a reality, just never you can modify your codes.
So this for loop is looping through 2D.
This one is currently looping through 2D because you have defined your temp extends to be 2D.
Okay.
If you just change it here, no? Okay, so suppose I said that, you know how to make this code completely dimension independent. So suppose I don't have this explicit 2 element thing. Now I can, if I just go here, you know, and suppose this is also fill. Now you can just keep changing this to 3D, 4D and so on. The code will work, compile.
Okay. Okay, what happens like if I want to go through only one direction, like only x-axis?
But then you write your normal for loop.
Okay, not for normal for loop.
Yeah,
okay.
yeah.
Okay.
No, here, Somidip, we can do that zone min of 1 also, no? 1.
Yeah, you can, yeah. Okay, if you really like this so much, then yes, please. Okay. Well, the problem is,
Okay.
the problem is, well, then you have to create your zone like that essentially. Means you have to create a 1D zone. The way you can create a 1D zone, I'll figure out. Okay, how do you create a 1D zone? You really want to do that? Basically, you can do it.
No, I'm just asking. I'm asking instead of writing this one for loop, you can write 2 by x equals zone min of 1 and zone min of 2. Like that also can be done, right?
Contains, so see, you can write zone min of 1. It will give you a integer, single integer. Then zone contains expects a coordinate, not an integer. It will give you a compilation error. Because this zone is a d-dimensional zone, not a 1D zone. That's why if you want to use integers, your zone itself has to be internally 1-dimensional. Then what you can do is you can do a take. Take basically reduces or projects the n-dimensional object into m-dimensional object here. So this will take a 2-dimensional object and extract the first coordinate out of it and things like that.
Okay.
You can do it, but it's unnecessarily complicated. If you're
Okay,
doing
got it. Just do it regular for loop and just use. Yeah, cool. Yeah.
Is there a particular use case where you will be using only, suppose, n-1 for loops? See, you can do n-1 for loops instead of creating a full zone. Here, you can call the get zone, which will give you the full 3D or whatever d-dimensional zone. Then what you can do is, see, this box basically has a min and a max. This is essentially a bounding box. So zone, there will be a min and a max. So you can just modify the min and max here. So instead of calling, so let me call this the zone D, full d-dimensional zone. Zone 1, which is one-dimensional zone, will essentially be a bounding box or a U box, because this is a integer, unsigned integer coordinates, where you give the, basically you can create your own zone like this. Essentially, if you want it to be so temp min 0, 1, 1, and temp max 0. Then you can use it.
Oh, okay. That's a one-dimensional zone.
It's a one-dimensional zone.
Okay, I mean, cool. Yeah, but
can do it. Or if you want a 2D zone, then you just put.
Right.
Basically, these are like slice views, essentially.
Okay, right.
Okay. So there are better ways of doing the same thing. You can minimize this ugly syntax a little more by doing. So see, temp min. You just want to create a new temp min, okay? Which is basically the last axis replaced with 1. The way you do it is constant auto. My new min is temp min set. What is your axis? 2 set to 1.
Oh, okay.
So this will, temp min will give you a 3-dimensional coordinate. And if you want to set only one particular component value to some other value, you can do it like this.
Oh, okay.
The only thing is, set usually modifies the value in case. So this is the thing, it will do this. If you don't want to modify temp's value, which you can't technically because you've already defined it via all these things, then what you can do is you can make a copy of this on the fly. This is what Python uses usually for arrays. And then assign it. Then it will create a new copy of this same thing and then you'll assign it there.
Okay. So basically using all the zone thing, you can take slices from blocks and stuff.
Yeah, exactly.
Take subsets of blocks. Okay, nice.
Yeah. Okay, so this is my new min and new max. Or you can put that because syntax here only. Max would be similarly. So yeah, this is a 2D zone and so on. So let's get back to our 3D problem. By default, you will get your zone by doing get zone. And if you want to, this is for iterating over the physical part. If you want to iterate over the padded points also, including the physical points, like the entire thing, get zone padded. It will effectively, this min will essentially internally be min padded of your block. Min padded, the minimum of the zone is the min padded of the block essentially. So this is the standard syntax you'll see everywhere written in your codes, whatever solvers you're writing, whatever has already been written. So this is clear, this for loop syntax. Initial starting condition, this is what you initialize. Then at every iteration, after you're done with whatever you're doing internally, you come to the last point and increment. And then before you go into the next iteration, you check whatever is the middle condition, is it true or false? So zone.contains returns a true or false, depending on if x, the incremented value of x, still lies within the bounds of this grid. If it goes out, it will become false, it will exit the loop. So this is how it's done. And if you really want to see whether it's true or not, we can just dump it and draw it in GNU plot. let's not plot 100, 100, we'll plot 10 by 10. That's easier to see. Okay. So if you really want, so let's do a, not no plot, we'll do paraview. That will tell you a bit about IO functions in this thing also. So how do you do IO of grids? Let's see, include SSLABS IO/IO.h. IO basically has VTI writer as of now. We don't have CSV writers and all those things, or VTU and all those, because VTI seems to be the smallest or the most efficient way of packing things. Later on, we can, like, there are plans to include different formats and all, but it's still under review by different groups. Okay. So IO, how do you call it? So VTI writer is simply SSLABS VTI writer. You can open a file. Maybe 1 minute, I keep forgetting the syntax for this. Anyway, anytime you forget a syntax, you can always go to these example codes that are there, or even in your package only it will be there. Package you downloaded. You can go to, for example, simple one is what STL2 marker or flowering, let's say. Just ignore all these things. At the end, you'll have VTI marker. Is this a, okay, this is a multi-resolution example. STL2 marker. Single resolution, simplest example of them all. Look that simple, but okay. So what you do is, SSLABS VTI writer, you give the file name. What will happen is, it will just append a .vti at the end of whatever you give here. So it will be marker.vti. Well, technically not. VTI is usually represented in paraview VTK formats as one VTI file represents the data of one block. So if you have multiple blocks in a grid, you'll have multiple VTI files, and the meta file combining all these files together is called a VTM file. So if you write marker, it will generate marker_0 for the BIDX or block index 0. So it will be marker_0.vti, marker_1.vti, and so on for each of these blocks. And then it will generate a marker.vtm, which will contain or encapsulate all these blocks into a single file. So you can, in paraview, you can just load in marker.vtm to show you all the blocks together. Okay. So we are currently working with only one block. So let's stick to VTI one block itself. This is by default parallelized. So we'll just give rank 0 here because we are writing a serial code. And then what you do is, you open a file. This VTI, you can name anything, like my writer or something, whatever you want. So it doesn't matter. It doesn't have to be VTI per se. I like to use VTI because it's small. That's all. Then you open the file. So you open the file with which index? You will open it with, see, there's a rank being called here and the index also being called here because it might be possible that later on you want to pack multiple blocks into a single rank itself. Okay, that's one way of doing domain decomposition within a process itself. Okay, that's why this one represents the MPI rank and this one represents the block ID actually. So this is actually the BIDX. Okay, so I'll call the BIDX. So there's only one block, so BIDX by default will be 0. Okay. The VTI, then you add whatever field you want. So add block. So here our block is temp, or I think it's add scalar block, I think. Yeah, add scalar block. If you're having a scalar block, it can reduce the template type, but initially when we wrote it was explicitly add scalar block, so it's legacy code. Later on we'll add just add block, it will reduce the type of the block on the fly. So, and then you to add block, you not only give the temp, but you can also say what is the variable you are like. In paraview, in one of the menu bars, you will see the name of the variable itself. So here we're doing temperature. Okay, so you can in words write temperature, and then that's it. And then you close the file. So, that's it. That's how you write a VTI file in using SSLABS VTI writer. Okay, so let's write that and see if it's actually 80 everywhere. Anything else I need to do here? Nothing. Okay. Oh, our main is not defined. If you don't want to define argument, you can just remove that argument from the constructor. If I run this, oh, wow, what happened suddenly? Okay. This is the first bug you will find the first time you try to create use SSLABS code, a segmentation for. But as a good coder, what do we do? We use wall graph. Tool is memcheck. K.out. It says something, the address 00 is not stacked, malloc, or recently freed. So it says something has not been malloc. What is the error? So,
Allocation.
yeah. So the thing is, here we have defined the grid, defined the block. Then we have started assigning things here. Ideally, it should be the case because when you use a vector or something, you can just define it and then start using it. But in HPC type of codes, you will see that it is usually not a good idea to initialize or allocate memory the place where you're defining it, because you might be creating the metadata or the basic structure of the code somewhere in a main driver function, but you're going to start your parallelized load balance run somewhere else. So if you start allocating memory and mallocing inside this only, then it might not give you the most efficient distribution of data across RAM channels, whatever you. This is my value. Already there's some problem. Okay. As we were discussing, right? Like I might initialize something here, and then after load balancing, my block might be allocated to the process here, and so on. So then it has to keep fetching data from here and here and here. So in SSLABS, always the declaration or the instantiation of the object of a block and the memory allocation is user defined and separate. So whenever you define a block or create a block, no memory is allocated for it. That's why if you just create a block and start assigning values, it will throw a segmentation fault because there's no memory assigned to allocate anything to. So what you do is you have to, wherever you want, means here's a trivial example so you can merge them together in the same place. But wherever you want to finally allocate and actually create the memory consumption, you would call alloc. You don't have to call a free here because the C++ object will automatically free up its own memory allocation when you're done using it. Okay. I don't think it's magic like basically when the destructor is called, it will be deallocated. Destructor is called whenever this temp function goes out of the scope of the function it was created in. So there's a precise definition to when it will be freed. It's not like magic that it won't know randomly when you want it used and not used and so on. Okay, so this is it. So we'll recompile again and run. So it didn't print anything because we commented out everything, but we see it has created a marker P0 VTI. It's not created the VTM because it's only one single block and we didn't call a VTM right around it. So if you look at a marker.VTI, it looks like this is a standard VTK format. Okay. So you have the metadata here of the extent of the block, and then you have the actual values. So here you can see almost every block is written as 8000, and it is written as everything is written as 800. Although, okay, fine, let's print out. Everyone knows how to visualize using ParaView, or quickly I'll load it and show you that it is indeed 000 everywhere. My ParaView is a little ugly because I'm using NVIDIA graphics to render it, and the resolution sucks a bit. Source. Where did I create it? Where am I creating it? Tests. Okay. So it's a thing where if you see it is just 80 everywhere, as opposed to, let's do something. If you actually look at the data access grid, no? How do I make it? I have to basically change the resolution of my screen for this ParaView to, basically I'll tell you what it is saying. It's saying that this corner point is -1, plus -1.5, plus 1.5. Okay, which basically represents the real coordinates. Okay, the real coordinates of the minimum physical point, which basically means this block represents the block, this yellow portion. Okay. What about this halo portion or the padding point portion? Why is it that not being printed? You can print that by default. The VTI writer prints only the physical portion of the block. If you want the padded portion, just send the slice view or the zone or extent that you want to get printed. So if I want padded points also, I'll say get zone padded. Okay, so this is where the slicing comes useful. If you want to slice only half the grid or only a top portion of the grid, so you can pass whatever zone.
Nice.
So we'll compile it again and again run it. So ideally, what do we expect? Oh, sorry. We expect. Yeah.
Somadeep, can you just print a portion of the grid into VTI? Say, for example, you're looking for a bug or something like that in a particular area.
Yeah. Okay. So suppose my zone is, I'll create a zone myself. So U box B. What would you like? Let's say 2, 2, 2 to 5, 5, 5. Huh? Okay. This batch we are going to print. So let's pass this one. I think this will be conflict. So let's call this print zone.
So this is a physical. The 2, is in index
in
or
the physical. It's the index. It's the so min here is 1, 1.
Okay.
Oh, sorry. There's a 2D code. So yeah. Sorry. So this is min is the first physical point. And as we saw, that was because our numpad was 1, the minimum padded point was 0, 0, and the first physical point was 1, 1. So 2, 2 is the second physical point. Okay. So in terms of the picture, it would be just offset from the first physical point by dx. Here. And 5, 5 will be somewhere here. So this batch we are going to print. What is the batch? We're going to print batch like this. Okay. Yeah. So we'll print that.
So instead of the VTA zone, you could have given that zone also there and.
Oh, did I not give
the same?
Oh, the VTA zone. Yeah.
No.
I'm just saying, this zone is the big one. Huh?
Like that. Okay.
Sorry, SSLABS. I usually prefer to always scope my things. I don't use using namespace SSLABS because in header, I usually write mostly header files. That's why in header files never using namespace because that will basically everything will start including using namespace whatever you're including header files because other files include header files. Right? In CPP you can include do using namespaces whatever. BTI was not declared. What did I do? BTI, right? Oh, acha. No mistake. And now this new marker, so I'll go to spiral view, or I'll just delete this. Open up new marker thing. Okay, you won't be able to see much of this, but let's take a wireframe and you'll see how many points. So 2, 3, 4, 5. It's fine. Like, are you able to see the wireframe or surface? This color scheme sucks.
Yeah. So there's that subset basically, yeah.
Yeah, it gives a subset. And if I print the bigger one, then it will give the superset. So if I print the full one, so if I print with instead with the padded zone also, then only the middle regions I'll get 8p, the outside regions I'll get. So let's do that. Let's do the exact way we were doing BC conditions and bulk conditions. So BC was, so zone padded I would say is this, and zone is just this. See that 3-4 lines of code got reduced to such a small thing. Not each loop was becoming 3-4 lines and so on. Now it's very simple. So, and here what I'll do is I'll remove this VTI thing and I'll just give the full zone. So that will basically be zone pattern. So then we'll see a thin layer of boundary condition points also, which represents the padding points. already officially passed the deadline for the session to end. But here you can see the outside region is 80, the middle region is 10. And if you look at the wireframe, you can see how many points are there. I know it's very thin. Line width I can change a bit.
Yeah.
Looks nice. So this is how you do writing, IO writing in SSLabs code. Now let's quickly. So is this clear? Are these functionalities clear?
Yeah.
Okay. So can we just break for 5 minutes? I need to take a call. Then we'll come and finish off grids and we'll do grids and STL to marker. Then only for people who need multigrid, we'll do multigrid. Because I don't want to confuse other people who are not using multigrid with multigrid jargon. They'll think this lab is a horrible library. Okay. So let's just take a 5 minute break. I have to take a call because this one person is calling me 5 times now. Okay. I'll just take a call. Let's discuss whatever you want or complain about this lab library to each other.
Hey, if we are going to take longer time for those grids and all, then we can take maybe a lunch break itself now.
So the problem is I have a meeting with Intel at 2:30, 2:30 to 3. So can we, whatever remains, can we do it after 3?
Hey, Soumyadeep, can we do multi-grid someday else?
But you wanted multigrid, no? No, we'll do multigrid. I'm just saying the timings we have to figure out a bit. So basically, I can do it anytime you want, except today from 2:30 to 3 or 3:30. Just.
So someday else, because today I have my sprint meeting. So.
Oh, yeah. I told Jaju, yeah. Oh, no, okay. Jaju means Sundar. Okay, fine. Okay.
Soumyadeep, we can do some time next week also, like some other time we can reschedule.
Okay, fine. Okay, then let's do one thing. I'll take a 5 minute break quickly. We'll come back and at least finish grid creation with. So basically, I want to show you how to create a grid with multiple blocks, and then how to run a STL to marker over it. That way, at least the geometry part will be done. And you can do all your graphics rendering and so on, game engine and so on, development by yourself. Okay. So I'll just give me 5 minutes. I'll be back.
Sure.
Thanks.
So the area you guys use the core and all, how much of it then?
Yeah, these days I'm using. So we are working on this fluid particle coupled solver. So fluid gets solved with LB. So LB uses core.
Oh, okay. And then you have your DSMC part at the.
Not DSMC exactly. It's particle code. Yeah, slightly different. Yeah.
Sorry, which one?
Particle code, slightly different.
Okay. Yeah. Okay. So that is that doesn't have a grid at all. No? It's just tracking particles.
Yeah, but particles still need to be contained within individual blocks. Yeah.
Blocks.
Yeah. Sorry, I'm back. And my network connectivity is really bad. It just stabilize a bit. Interesting. So when I was running ParaView, was it becoming okay? Everyone can hear me, right? Right?
Yes.
Okay, fine. So now what we'll do is, now that we have created one block and printed it, and we have seen how to allocate memory for it and assign values to it. See, now it's clear how to even write codes, right? Like for example, now if you want to do an update of that thing, so let's do that. For int t equals 0 t or s, we were saying samples, but this time stepping, so let's call it time stepping only. So this is your n times plus. It's very simple. Now you don't have to keep writing for loops like this. You can just define a zone outside once, or you can define it again. Depends on if you want to break it down into functions. And here you will just do temp new. So basically, you have to create another grid, temp new. If we or do it the usual way of finding a difference. Alloc. So usually people alloc just before they actually require the thing. That way it's close to the data processing, so the pattern of usage will become similar to. Remember that it's similar to what is required. That's CFL into temp. Now the question is, what does this mean? Well, you can do multiple things here. One is you can break out. See, x is now a coordinate, a vector of coordinates or an array of coordinates. You can simply do x of 0 to get that thing. We'll do this thing. The other way is you would have liked to do something like this or something like this, but just remember that all these local coordinates are unsigned coordinates. So doing a minus on an unsigned coordinate is a bit risky if the x value itself is 0, 0. This will create a nuclear gantry. Okay, so best not to do. If it was something like this, it's fine. This is fine. This is fine. But doing a minus on an unsigned coordinate is a bit risky. That's why either if you really want to use the vectorized notation, you can cast it to an unsigned coordinate and then cast it back to unsigned. The way you cast it between different coordinate types is, suppose I have a unsigned coordinate which is num, auto num. I want to cast it to real num. Like I just wanted to make it double. That's it. So real num will be 2 R chords. Okay. If you wanted to make it integer num, suppose, sorry, this will be auto. I keep using constant because it has become a habit. Just ignore that. It has become a habit in the sense that whatever is supposed to be constant, I keep a constant. Only when you need something to be variable, you don't put a constant. Because whenever you put constant in C++, compilers find it easier to compile the code and optimize it because it knows you have promised it will remain constant. So it can do much better optimizations. So yeah, anyway, it's up to you. This will give you integer coordinates. On integer coordinates, you can do all this nice I-chords, voila. So here you can put 10 minus 19 and all this. See, you won't be able to put a minus in num. Actually, that is why we use U-chords for all this, because it guarantees that you don't enter a negative number or something like that here, or the local x coordinates don't become negative and things like that. So that's why we keep using whatever is not supposed to be negative, we use unsigned for that. Whatever can be negative, you can use integer, int for that. Or whatever is not supposed to be negative and can be large, we use size t, which basically boils down to in most compilers as unsigned long, a 64-bit unsigned integer. So in that sense, this technically time should also be std size t. Otherwise, you're violating, or you may be a quantum physicist. So this is how you like convert between coordinates to your card. So basically, if you want to use the vectorized notation here, you can do I chords here, convert the term this thing x to integer x, then do minus of 1 comma 1 comma 1, and then convert it back to chords. This is some people actually prefer this over that x0 thing, but because you know why? Because well, there's no reason why. Instead, we'll just do the simple way where we call x0 minus 1. Because once you pick out x0, it is up to you actually. You have to ensure that you have a padding point, otherwise minus 1 will blow up, like Vivio nuclear Gandhi. Just ensure that whenever you're using a stencil based code like this, please set the padding point to an appropriate value. Otherwise, you get nans and nans somewhere. X1, X2. These are the broken syntax. So there are two syntax of accessing data, as you can see. One is where you explicitly give the individual coordinates, or where you give a vector itself, which basically is like this, a single vector. So here, when we are doing this syntax, single x, it is actually this vector coordinate. This x is basically x comma y comma z, or I comma 0. Otherwise, you can do it individually also. Both are there. Usually for performance purpose, this is the best. The unwrapped coordinates, because then the code doesn't have to keep unwrapping the components individually by itself. You are doing it for it. This is shorter, but it is a bit slow. So for performance critical portions, don't use this. Try to use this. But anyway, for performance optimization comes as a second step. First, you get the physical correctness, then you get to performance optimization. So it's okay. For your quick development purpose, you can use the shorter syntax. That's one. And then let's break it out like that. It's easier to understand. Oh, why am I keep writing 3D codes? I'm so used to it. So first temp x0, x1 minus 1. Plus 1. Or you could have gone back to writing it as x itself. Yeah, this looks fine now. And the other step is you usually do a swap. Now, as you remember, we were doing a copy back from temp new to temp. Here, we will do a very simple thing, which we can do in the normal arrays also. We'll just do it shorthand here. Instead of doing an actual copy, we'll just swap the pointers. Fine, let's not do all this, right? Because currently I don't think I've given facility for that, because we don't swap pointers randomly here. The reason is, anyway, we don't need this operation in current LB codes because we're not doing swaps of huge arrays anywhere. The reason for that is your T new could be here, your T them could be here, and if you're swapping, then it'll screw up your performance on those. Anyway, for most of the codes that you will be writing in the company, this is single array codes, not double memory codes like this. So we might include the swap functionality as a aesthetic thing, but it's not required as of now. So we'll just do a simple thing here, like the way we were doing previously. Temp equals.
I think we have one requirement, but yeah, maybe.
Like, where? Tell me. Okay, fine. Create an issue.
Oh yeah.
Always create an issue. Otherwise, I also keep forgetting. There's so many issues in life. So this is n times. N times you have to decide. So the way we are deciding n times is Okay, see, you were doing this first. std arc 1. Oh, sorry, it's not std arc, ATOI. Technically, you can call it ATOU or something, ATOL. I don't remember exactly what it is. Or unsigned long. NT. Now I remember it was NT, not n times. Call it anything you want, but this was was 2. I'm trying to just recreate that same code. Huh? We should get the exact same output also, which is supposed to be 80.6002 was the reference value at 1,1. I'm trying to go for that. So for that, technically, we don't need to define res or armin. If you don't define res or armin, by default, the grid defines a default value for you, which is res is 1 and armin is 0, which is fine enough for any person. I will we'll keep that. So that's it, right? So after that many time steps, we will get a nice temperature profile, hopefully. Or we'll see how many time steps. We'll do that using command line. And to get the command line argument, we need to int gc star a vector of characters arrays. So okay. Error will come. Where is the error? CFL. CFL, what did we give? 0.1. Number I usually use. We'll say 0.5 is playing it too close and risky. In 2D, it can be more, no? How much can it be? Yeah. So how many? Billion. 1, 2, 3. No, billion will not make sense. So what were we using previously? 100, huh? In the test cases, yeah, test is here only. Let's see. Vim test update. We were using 12 cross 12. Achha, huh? And by the way, we have to print that reference value also. So before writing, we'll print the reference value. Reference temperature equal to temp 1,1. See, so simple. Sorry. How many time steps? 10, huh? What? Still? What? No guesswork. Well, grind. Check. Not malloc. Where? Which is what is not malloc? Where did I not malloc what? Malloc, no? Correct. Why did I try to trying to act smart and screwing myself? Yeah. Thanks. Oh, what failed? So something failed. Nice. So by the way, a good thing is if you don't, if you compile like this, it will turn on all kinds of internal checks and it will throw errors if some internal consistency has been failed. Huh. So if you don't want to turn on checks like this, you can pass a dn debug. Usually in production runs, when you're compiling with CMake, this is already there in the release build type. But right now, since we're doing a test case, it's good to have these debugs. So what is it saying? It's saying that assertion t-val is less than num replicas failed. So how much is my num replicas? By the way, where is the num replica supposed to be? Right only. So, oh, okay, sorry. Just give me 1 minute. Small modification to the way I am trying to run. Where are you coming from? This is weird. Num replica. You're very silly mistake. You'll regret in the next 1 minute. I'm using a 3D coordinate somewhere. That is the problem. Where am I using a 3D coordinate? Am I? Nowhere, no? We'll just put a check here. Put till here. And we'll put another check here. This is the only thing we had added, right? Must be here only. And something else. Something else changed. By the way, as Mrinal had suggested last time, we should only copy the padded region here. That is not the error, but okay. Note. Oh, it's after that. Okay, interesting. Very interesting. So it's here. What is the problem? Supposed to be here. That's weird. Am I doing some mistake I'm not seeing? So if I move this, oh, so, okay, that is not the mistake. Let's go somewhere else. Oh, okay.
Temp new equals temp.
Temp new equals, no, here it will
I mean,
reverse, right? Yeah.
Okay. You have done temp new here.
Yeah. But it's very weird. What is exactly the... Oh, I think the issue is... So, this is X. It's a 2D grid, right? 2D grid.
X of round bracket 0? Or
No, that is square bracket.
that's square only, right?
Just give me 1 minute. I'll quickly check one small thing. Oh, wait. You know what? Maybe I forgot to put a bracket somewhere in the middle. No, that is also, that would have given a compilation error. This is weird. So this will pass. Now the question is, this bracket syntax is somehow not working. Although we have been using it for the last 3 years. Suddenly now it decides to fail. That horrible thing to do to me. Syntax is failing. Why is it failing? Because doing something really, really weird. It's a scalar grid, which is true. Let's look at scalar block. Yes, understood. Where is it? Where is the scalar block business? Scalar block. This is so weird. Like I'm not being able to see the bug.
So what is the bug? Like,
no, so basically
what
it's saying that this syntax is, where is it? Where did it go? It's saying, oh, no, not this one. It's saying that this syntax is invalid. Oh, not invalid. It means something wrong is happening. But this is the syntax we have, every code is using right now. I'm just not being able to see what exactly is the problem. Is it because the wait. Just did that to take out the assert. Okay. Let's see. Because since people have been testing with without assert, there might be a small bug somewhere. Anyway, we'll just get back to doing this. Good to hear business will leave because we know exactly where the problem is. So compile. And it is 24, which is not correct because 10. How much am I initializing it with? 80, no? 80 and 10. So this one, we have to find out what is the issue. Just give me 2 minutes to figure out. A very silly bug going somewhere, then we'll. 6. Sorry. Tgrid is here. Oh, this is a very nice thing. So, for some reason, my bar index is taking this up. Okay, I see. So there is a small bug here for the 2D case. It is assuming that tval is a replica, whereas it is not. Means it's using a 1D formula instead of 2D formula. Okay. It means basically it's thinking this one is that replica thing, not the y coordinate and so on. So what we'll do is we'll equivalently just go into 3D case just to show you how it looks in 3D. But since we don't use 2D so much, it's a small issue. As we said, not much change except here, if you're breaking it down for performance reasons.
So for 2D case, can you do like 1, 1 and 0 or something?
Yeah. So that's exactly what I'm doing. Okay, so for that, we just do it like this. So, 1. So basically, it's a 3D code with a Z direction being 1 point. Right?
Yeah. So in this, you were saying it was taking that as a replica, the second one, the second argument.
Yeah.
Oh, so you cannot call SSLABS with writing a 2D code, you're saying? I mean, you can do it like this. Yeah. Okay.
You can do it like this, but yeah. No, so basically, I have to just remove this condition.
Got it. Okay.
It's a hangover from some copy paste issue somewhere. So, okay. Actually, no, I haven't analyzed it. Let me think about it a bit. Right now, I don't want to think about it. It might not actually be, it might turn out to be actual constraint. Because otherwise it would have shown up somewhere. Anyway, so these are the 2D cases. And everything is 2D. See, that's the nice thing. If you just change this, and if you don't hard code much of things, it will automatically go through for 3D also. Yeah, that's the only change. Oh well, your formula will change to 6 here. That's the only change. That's it. If this also fails, I should seriously reference is 0. Why? Are we not doing this change thing? Oh, acha. Should be 1. No, there should be 0. You're putting a padding point, so technically, yes, there should be 1. It's effectively 2D code, right? So why did I change this to this thing? And 1. 4 point this thing. Where our CFL was what in the previous case? 0.1. CFL was 0.1. No. CFL was 0.1, and that was 12. And what did we take? 12. Oh, acha, by the way. So this is 12, there was the total size. We are taking our argument to be the, so okay, if you want to give the same arguments, then NX here should technically be plus 2 or minus 2. NX is the actual physical point, so minus 2. Yeah. Okay. Now it would make sense. That is okay. So we were using 10 points to see where the replication is getting lost. This is 10. Oh, temperatures were 10.
10 by 4.
10 by?
The number, like you're running with the MPI run this one, no? If we give.
No, this is serial code right now.
Oh, this serial, okay.
Yeah, just like the previous one. Yeah. I'm trying to check where is. This is fine. It is going on here. The ones are giving correct values. This is correct. It's supposed to be 10. If you're doing 3D like that and with padding points, are we supposed to, let's put the padding point to 0 for the Z axis, huh? Maybe then it will be fine. Resolution is okay. That's fine. So we'll print this thing. We'll print where my cursor go. Since this is PC and bulk. So 0, 0, and now this will be 0 because there is only 1 point, no padding point also. It should look fine. First one will be 80, second one will be 10. Okay, that's good. So now the only change is happening here where I'm expanding like this. So basically, what am I doing? Mistake here. Let's quickly, comment this out. See, just doing that. It's the sad process of debugging a code. In live coding, worst thing. Reference PC temperature is 0. Is a problem. Because I can either do this. Why is my reference PC temperature becoming 0? That's the fun part. We'll just bypass that by quickly doing a temporary thing. Sorry, looking in the middle of nowhere. Okay. So basically, this transfer was not happening for some reason. Because I was going from so on. Let's quickly look at the update code that we had. Sorry. So this will be src. Oh, okay. I was not supposed to do that. The previous thing was correct only. Why did I just change it like this? Like, yeah. Okay, sorry, my bad. This was my mistake. Wrote wrong code. So everything was wrong. Okay, so we are back to this. So this is fine. This will give us the correct result. Expected. Now we can dump that other thing as well. This was not needed because we did not have this in the C code also. Okay. So we'll just go back to. Can you just give me 1 minute? This is really bugging me. What is this trying to do? Okay. This is my mistake. It should be d equals 1. Okay, I'll change this. I want to see how a process of changing debugging happens. Like a addition. So this is a workflow. This is a good example of how real life code development happens. So someone can put bug in var index for 2D. Basically, it will be 1D also, 1D and 2D, and 2D secret. And write a description. So basically, you can either, if you're getting an error, you usually post that error. So I'll just copy paste this and copy paste the portion of the code that was giving that error. So say that sample code portion is this, and the error fix this. Compilation. I'll support that because sometimes the error might be also in a compilation. So usually this is the way. What would be here? So this was the portion which is giving me the error. Or you can write this also, it's either way. Like I'll write this because then I can quickly relevant portions are this one. I'll just quickly make it 2D, because that is what was causing the so this one changes, this one changes, and what else? Okay. So this is the error. Now what you do is you assign to me usually, and I'll put a milestone and then I'll put a bug label on it. And I'll set a due date. So due date is today early, right now, in front. There we go. So once this issue is created, you create, I'll try to see if it is a valid issue or not. In this case, we have tested, it is a valid issue. So we'll have to quickly resolve it. So we'll create a merge request. Then I'll open up the code. So right now it's very simple. So I'll just do it online. I won't copy paste, download it anywhere. So go to libs, grids. So wherever that code is, dgrids. Essentially what it's trying to do is when it's going to call this operator with this should be 1. Simple bug. So only when it is one dimensional, then the first coordinate is the x coordinate and the second coordinate is a replica. That's why it should assert that the second coordinate is less than the total number of replicas here. If it is else, if it is 2-dimensional, it should assert that the t-val is greater than equal to the min padded of 1 and it is less than max padded of 1, which is correct because t-val will become the y coordinate then. Okay, so then this is the simplest change. See, bugs are like this. It takes days and millions of dollars of loss to find bugs like this. Like that yesterday I was saying, that Microsoft error 0 equals or equals 0. Like that. One line change, one word change. So commit and then you say fix treat eval in 2D 2 args case as y coordinate for y for 2D C or hash 155. So once it's committed, then I'll go back and I'll look at my merge request. Now there will be a code review that will go on here. So people will see what are the changes I've made. There's only one change, and then you'll such a nasty little bug it was. Start a review or something. Since I'm the only person doing this, I'll just submit the review. And it'll say one unresolved thread to me because it says this thing. I can either create a new issue out of it and then start solving those issues and merge back to this merge request, or say it is simple enough. So I'll say, yeah, it was done fixing. And then comment now. And this resolves the thread. Okay. So now that it's resolving the thread, all threads are resolved, it's saying. So I'll mark the draft as ready. Go back to overview and I'll approve. And then I'll merge the pipelines when pipeline succeeds. So what this will do is this will trigger the pipeline whole thing. And okay, ideally, well, if you find a bug, I should have done this here right now as a good example. Whenever you find a bug, ensure that you write a unit test which captures that bug. So ideally, I should have done a 2D debug level unit test for this 2D array, 2D indexing also. I did not do that here. It was very bad because I was trying to do it quickly. But so now it's essentially it will go create a pipeline. The whole workflow will start now. So as you can see, it's running. It's created the builds. Now it is testing all these things. Okay, this is a test case. Then the final, when it is, what do you say, going to merge to the main branch, it will run another test case. If that test case passes, it will deploy that new code in the latest folder in packages here. Okay, so basically you will see that from 13th July 9:10, it will update to something like 16th July 13:10, 18, 13:20 or something. Okay, so till then, what we'll do is we'll continue with our examples here.
Samitip, I had a question.
Yeah.
So this entire process that just happened,
Yeah.
This has a log, right? It will have some log saying that this was like this and this became like this. Git log or something.
You mean which code was changed where?
Like right now you changed that file, right? And you gave for review and
yes.
You just saw that line and you you agreed or whatever for commit. Yeah. So that entire process you merged it.
Yeah.
So yesterday I was just going through just these commands and Git commands, and there's another thing called rebase, right? Where
yes.
Where you rewrite your logs also.
Yes.
So what should that what if this happens?
Rebase is usually not used very commonly. Rebase is usually used if you really want to delete some history of in Git itself in a very weird way. So basically there is usually rebase is the most common use of rebase, and the only legitimate use of rebase is suppose you accidentally committed a PDF or a whole DVD rip or something like that. Okay. And now Git will store it in its history, and then your whole Git repo will be 1 GB big, and so on. So now you want to go back in history and delete that commit as if it never was done. Okay. Then you have to check out to that branch, and then Git rebase is one of 5 commands in a line of things to delete history in Git. Yeah, that's the only legitimate use. The legitimate use is you download the thing, you do Git rebase on everything as if you went back to the first commit and then push that new thing here. That will basically erase everything, including the history. Yeah.
Right. Okay. So I mean, it should not be used.
No, there are legitimate use cases. If that is the case, yes, it can be used. It's just that it's a bit, it's like bomb. Like when wielded unwisely, it can create havoc in your Git repos.
No. Yeah. I understand that part, but I'm just saying that like a log for your code, do these sort of like roadblocks and all, even the history you can change it, right? Because those are irrelevant in some sense because you have moved past that.
Yes. See, there will be, even if you change, there will be a signature that you changed it. What was changed that you can erase, but that you erase something that will be there still. So it becomes a cyclic process. Like you have to erase the signature of erasure, and then that will itself create a signature. So yes, miss. In that sense, it's possible to figure out if there is tampering, but someone who is smart enough will be able to just delete the contents. They won't be able to hide their signatures.
Right. Got it.
Usually, most people who go into doing nasty things, they actually brag about their signatures. They leave a trace that I was here. So that is okay. That conforms with the Git philosophy. That you can delete the content, but you cannot delete the signatures.
So basically merges.
So yeah, so basically if you go to commits, for example, you'll see all the history in a linear way. Or that git log pretty one-line graph that you can generate in the command line. That also shows the same thing. Or if you want to go to the graph. So if you click on any of these parts, it will always give you a snapshot view of what the thing was changed and so on. So in this commit, these things were added, right? Is that what you're asking?
Yeah. Exactly. Yeah. So these things won't be erased though, right?
No, this is also not be erased. No, well, let's know. Okay, that's a very generic statement. No, you can modify this sequence. So, for example, let's look at the graph. It's best explained by the graph. Suppose I say ki this comet introduced a very bad, huge file, 1 GB file. I really want this comet to go away because in the next comet I've deleted the file, but this history is still there. So in the history logs, my repo has become 1 GB. Okay. So even though the current state is not 1 GB, because of its history, the repo itself is still 1 GB because it's carrying its history. So how do I delete its history? So what you will do is you will basically go to the previous commit, branch out from here.
Okay.
Then so basically, if you go to something called it's a particular command which rebase only, yeah. No, rebase is basically get rebase, get rebase itself. If you do git rebase, it will basically open up a terminal with a like log file, which will show you from the place you are starting the rebase what all new comments you have applied. So in that file, you just have to delete the comment which you want to delete, and press enter. Then it will start replaying the entire thing again, such a way that it's as if you are applying the same next patches minus this patch on top of this comment, original comment that was there.
So all the previous ones are gone.
So basically, whatever the path was like linear here, like this will stay. It will create another branch and apply all the subsequent comments minus the comment you deleted.
Okay.
So then it will create a new branch. So that will come to a new state where that big file is deleted, but all the other patches have been applied. Now it is your choice to merge that and make it the main branch or not. In that sense, the previous history might still be there. It is your choice to.
Got it. So it will be a smaller file in some sense.
Yes. Okay, what were we trying to do? Oh, we were waiting for the pipeline to finish. Sorry. I think it's finished. Yeah, nice. So if you now go to this thing, packages, you'll see that it has been deployed freshly. We'll download a fresh version because the last version sucked. This keeps happening. Don't worry. I'm just curious, is anyone actually using 2D code? See, basically, since I've not got any complaints about 2D codes or this bug yet, it means no one has been using 2D codes.
Yeah.
or no. See, technically, this was
use 2D like 3D only, man.
that's the thing. No, see, technically, if you actually ran the code with -d and debug, the code would have gone correctly because the only place which was catching this problem was the assert. Okay. So if the assert is not there, the flat index calculation is actually correct. So even if you run the 2D code without the assert, it will be physically correct. Okay. It's just that there is I put my own logic to shoot myself. I try to be too strict on my logic. That's why I put that assert. It's a good thing. Asserts will help you find bugs like this. So it's a good thing to put asserts, but when you're doing production runs, just use -d and debug because you don't want to keep asserting everything in production because if you already tested the functionality of the code in debug mode once. So that's fine. Okay. We'll use this one once more. This is SSLABS business, this old one, and duplicate. And we'll unzip the new one. F SLABS. And we're in tests. We're doing tests. Now we can use the 2E version without any problem. Previously also we could have used, except we would have had to remove the assert, but now it's a good opportunity to learn something. Clean up your code. Remove all these X2s, not required. The worst thing will be if it fails again. Wait, that will be seriously sad. Just one minute, change everything. 2D, 2, 1x, 1, 1. Everything looks fine, right? Anything else that needs to be changed? I don't think so. Okay. Please don't fail. Beautiful. What? Like, so happy right now. So anyway, so we got the reference value correct. So now we can check the marker also, just in case you want to verify. What's the time? 1:30. This is the slope gradient. Let's do a bigger system so it'll look nicer. This how gradient Laplacian evolves like. So nothing to change here per se. We'll just launch with a bigger system size. So we can go quite large. Instead of this, we'll go to 200 and times it is 100. But genius! I deleted my execute. As you can see, I'm not putting -03, nor am I putting D and debug, so it's been very slow. So let me do that. -D and debug. So you have tested your functionality using D and using the asserts. Now you can do a full-blown release mode stuff like this. Dark, very nice. Temperature will obviously change because we have increased the system size. It just look good in bad view. That's all. Good. This new thing has started in the new beta view. This magic book user, very nice. Okay, so this is how it works, and you can apply the same principles that we have been learning about performance gains and so on by trying to see how much we can tweak, optimize, and all those things. It should come to your theoretical bandwidth the same way we were doing. So this is the functionality. We are just going to talk about the functionality of SSLABS code right now. So again, if you do this performance thing, it will take Saturday also, which I really don't want to do. So this is basically you created one block. Now I'll just quickly go over a grid of blocks. It will take 2 minutes, and ST to marker which will take 10 minutes. Just 15 minutes more. That's all. Then we can all break forever. Multi-grid we can do later. So for a grid of blocks, essentially what we're going to do is we are going to create something like this: multiple blocks in a single grid. So how do we do that? You have created a single block like this. You have to create a grid of blocks. So ideally, it will look like something like this: grid of blocks, scalar blocks. This should be a syntax called G. This is actually the syntax, except that you have to give all those extra tidbits here. So TD is the type of the block itself. Apart from that, there are two more things you have to give. One is the dimension of the grid itself. See, it is in a very generic way, you can embed a 2D block in a 3D grid. Okay, that's like what manifold embedding and things like that you can do. That's why it's written in a very generic way. So it is a D-dimensional grid. You can try to put an M-dimensional block in it. It will currently throw an error because I've put an assert like that or a static assert like that. But theoretically, yes, it is possible to do that. And then you put another T. This T I will tell later why it is required and so on. So basically, essentially, this T represents the actual nature of the variable. This T represents the data type which will be used to transfer the send-receive communication data between two blocks. Because MPI is a bit slower than RAM to cache memory bandwidth transfers, it is sometimes good to convert doubles to float and then pass the float and convert it back to double in the main memory, because float takes lesser space. So it is lesser data traffic when doing MPI communication. Okay. So ideally, if this was double, technically you can do something like float also. Or if you are suppose doing a very weird data structure, suppose you have a class here itself called myParticle, which has velocity and positions and things like that. Then MPI won't understand all those classes unless you define your own data type. Instead, what you can do is you can pack it into a linear array of like floats and pass that array itself. So that will be like an array of floats or some linear array of something, double star basically, or something. So that is also possible. That's why these two types can be different again theoretically. Right now, most codes use it as the same because that kind of performance optimization is currently not necessary, but it will become in certain codes that we'll see on a case-by-case basis. So this is fine. Now in a grid, what all parameters do you send? So whatever the size of the block is will be given by the scalar block. You don't have to give the grid the size of the block. Let the block decide how big it is supposed to be. Here you will just give the number of blocks. So to replicate this situation, what we'll do is we'll give 4 blocks in the x-axis, 2 blocks in the y-axis. So there will be 8 blocks in total. So we'll give 4, 8. What else? Technically that's it. Just quickly check. I myself have forgotten what the arguments are. Surprisingly, I don't use my own library. I just create them and leave it at that. Block grid. Okay. So num blocks, block size. So this block size you can give to grids if you want to automatically set the block size of the grid. So basically, see. Currently, for all LB cases, to match the offsets and so on, how the blocks talk to each other, especially in multi-resolution and so on, it is assumed that all blocks in a grid are the same size. Previously, that constraint was not there. Each block could have been of a different size. So technically, then it's a loose collection of blocks. It's technically not a grid of blocks. It's just a connective network of blocks, basically. So previously, it used to be like a network of blocks. Then, because of performance reasons and simplicity of usage and so on, for LB-specific codes, we brought in this constructor where you can specify the block size itself in the grids thing. So each block that the grid creates will be of the same size, which is given here. So this will become the num or the block size. Okay. So block size in this context is just the num that you are creating above for the block itself. And technically, this is num blocks, the 4,8 thing. It's not 4,8, it's 4,2. Again, bug I would have introduced. Blocks. And then what are the other arguments? It tells you, you get to choose whether the block is periodic or not. So if you fill all zeros, this is like an MPI command. Oh, I didn't talk about periodic in MPI, but okay, fine. If you fill all of the axes as 0, it means it's not periodic in any axis. If all the axes are given as 1, 1, 1, so basically, if here it is 1, 1, it means both x and y axis are periodic. If you give it like this, it means only x axis is periodic, y axis is not. This is like nothing is periodic. We'll use nothing because we are not going to need a periodicity for this problem. So periodic is SSLABS. To keep it in sync with MPI, we use MPI also has a concept of periodicity in certain topologies. So that's why it's I chords, because there also it's an integer array in MPI. But you can just pass this periodic array to MPI array also. That's why it's like this, without having to create another integer array or to do. And technically, you can't even do 2 I chords because it's going to be passed by pointer reference, not as value. So needs a solid memory allocation for it. Then you have res and resmin. Res here would be the resolution of the block or the grid, because whatever is the resolution of the block becomes the resolution of the grid. If it's a single resolution thing, in a multi-resolution thing, usually, or a multi-grid case, the resolution is the coarsest level resolution. The finer you go, the finer it becomes the resolution automatically at jumps of certain. Currently it's 2, but you can change it internally. Resolution and then Armin. Armin is the global Armin of the entire grid. So if this was the Armin of the local block, this would be the Armin of the entire grid. Let's say Armin of the entire grid is R chords 2 or D. We'll call it as -10, -10. So this is clear, right? Like this is the global coordinate Armin of the grid itself, which is basically here. And this one was the local Armin of the block here. Again, when I say Armin of the grid, it means it will see the like minimum point or the closest or like left bottommost physical point among any of the blocks. Okay, the physical point. So if there's a padding point, it will be rmin minus some delta x by 2 offset, or delta whatever number of padding points is. So this is it. This is the entire block syntax. Usually you don't need all these other things. This would be enough. So like this, you create your block. Now num blocks would be num, as we saw here. And then the thing is, now you don't have to create all these scalar blocks. Grid will automatically start spawning them for you from the syntax. So let's do that. So this also we technically don't need. Numpads we'll need, because each block technically can have different padding points, but don't use it because LB will block them. If you have some other use case, you can use it. Num is, you can just put this block size instead of calling it separately again and again. That's it. And nx here would be block size. Now, what is your num block? We have hardcoded it to 4,2, and this one is 1, 1. Periodic should be 0. We don't need periodicity. By default, I think it is 0, so we need not pass periodicity. Yeah, by default, periodicity is 0. So how do we create a block now? Now we have created a grid, the skeleton of this whole grid, the background gray area. Now we'll create blocks at different 0, 0, 1, 0, 2, 0, and so on. So how do we do that? Very simple. Here is your grid. We called it G here. You can call it grid or whatever you want. G, create block. 0, 0. Okay. We'll create a block. Create a block. Suppose I want to create 2, 0. Then 2, 0. Once you have created a block, just go to the block and allocate memory, because even if you create block here, as I said, allocation is kept separate for performance reasons. So you have to go to those created blocks and allocate memory. So how do you do that? Usually, there's a very shorthand syntax of iterating over all created blocks. See, ideally you could do this. I could go from int bx block 0 to 4. It's like a 1, 2, 3, 4 block number. This is not x, this is bx. Huh? This is the number of blocks I'm iterating over, not the grid points. So by is 2. Then we'll have, then we can check, like if G contains, or G, this block, we can check bx, by. We have a contains function. Confirm this is grid, and there will be contains has empty. So you can check if, oh, it is not here. It will be in the base class. So grid. Okay. So we can check if it contains some block index or not. If it contains, then we allocate. Then you do, how to access the particular block? You will just do G, whatever your block type is, bx, by, dot alloc. And if you want to initialize here itself, you will do G, bx, by is the block thing. And you can iterate over the, so this, you can iterate over xyz like this. So basically, you can put your xy for loop here. I'm just quickly writing this because this is a very nasty syntax. I'm going to show you a better syntax. Okay. So this is how you iterate over points in a grid, points inside a grid clockwise. Okay. Now, so many curly brackets and all those things. First of all, there's a big problem here. See, for exascale systems or petascale systems, the number of blocks that you will have will be huge. And on top of that, the number of grid points in the block will also like multiply on top of that. So you'll end up with a huge for loop. There is no point of doing, like just iterating over this only will take you 1 hour. Okay, this like bakwas timing, waste of time it will be. That's why I think Sundaras, here is the point which answers your question. Why is the block access written so in such a complicated way? Essentially, blocks are not stored, like this grid is not stored as an array of blocks of bx by by. It's not run like this, because then you have to iterate over all bx and by and see if each of these arrays actually has a block allocated or not. Instead, what we do is we create a map which contains the bidx and the block itself. The good thing about a map is that a set we can create. We can just create a set of blocks. So these are all standard data structures that you come across any programming language. A set, there's a basic difference between an array and a set. What is it? In an array, you can have something like 1, 1, 2, 3, like this. There can be repetitions. In set, there can't be any repetitions. It's unique. The second thing is, in an array, you can allocate a memory for, some n things, but only fill in a few of the elements with actual values. But the memory will be consumed for all the n elements, the entire size of the array that you have created. Instead, in a set, you can only push in and pull out only required elements. You don't have to pre-allocate a huge amount on a set. So in a set, you can basically have the equivalent set of this will be just 1, 2, 9, 1, assuming that these are like null elements. So null would be better thing here. So all these spaces that you are allocating for in the array is not wasted here. If you use a set, the other thing is also that repetitions are not allowed. If you want repetitions in your list, you have to use something called ST list. Or there are lots of other drill structures. If you really want to go deep into it, you can go to CPP reference and go to the container section of the CPP reference library. It will show you how many containers it has, like there's array, vector, DQ, and all those things. So each have their own utility. We use something called a map. A map is like Python vector, JavaScript, key value pair, and all those things. So essentially, what does a map do? A map will tell you the way the block allocation is done internally is we listed the BIDX here, no? For each block, BIDX 0, 1, 2, 3, 4, like this. We will just list the key value pairs of only those blocks which have been created. So if I have created this BIDX 0 block, which is 0, 0, I will say BIDX is 0, and I will put a pointer to the block. So the actual block PTR, I will put block 0 PTR. And then basically, when I'm calling this G bracket BXY, no, it is essentially calling BIDX, and BIDX is the key of this map here, and its value is block pointer, or basically a reference to the block, not a pointer, because we prefer not to use pointers. It'll be a reference. So essentially, if you call gbidx, it will return this reference to this block, and then you can work on this block like .alloc, .size, or whatever you can do. So this is how it's created. The advantage of this is it will store only the blocks which are created. So for example, this one would have BIDX2, right? So it will store like this. Where is the intermediate BIDX01? It is not even allocated because it's not created. That way, your metadata itself remains very short. Otherwise, for exascale systems, the metadata of creating, because the number of blocks in exascale system will itself be of the order of billions. The metadata itself will take at least 1 or 2 GBs, okay, or at least 10 GBs. Now, if you have 128 cores or 16 cores running on each node, if each process's metadata itself is 10 GB, you have wasted 160 GB there itself per node. Okay, so that's why we prefer to not use these kind of for loops, like serial for loops, as we call it, like or the standard C for loops, which goes serially across all possible numbers, and then do a if. We instead use a map which stores only the required metadata, not every possible metadata. And the way you iterate over STD map is for auto. So this is a key value pair, right? So essentially, each element is a key and value in this map. So G dot. So you want to get the B indices, BIDX, and the block references. So it is called B indices blocks. So here, in the key value that they returned, the first one will be the key. So the key is basically key value, whatever this, or if you call this element E, then the key is the first element of E, and the value is the second element of E. It's a pair. In this case, the key is the BIDX or the B index, the flat B index that you were calculating here. The value is the actual block, which you can call B or block or whatever. And because if you want to modify things, you have to copy by reference. So always put ampersands here. If someone wants to know what is copy by reference instead of direct reference, it means if you just do this, it will make a new copy of the entire block into B, which is very costly and also unnecessary. If you want to modify the value and store it in the same block, if you make a new copy, it will change the new copy. It won't change the old copy. The second thing is, if you're copying by value, then it will copy every element by element. So that's very costly. Again, it will be RAM, that whole memory bandwidth limited thing. Instead, if you do this, it's like just a reference. So it's not a new thing. It's just referring. It's giving a short nickname B to the whole block thing. B index is just a number, so it can be copied by reference. That's okay. And it's not going to be changed also. So ampersand are by references. So this, since E second is the thing we want by reference, its parent should also be copied by reference. Otherwise, if I do this, then it will create a whole new key value pair, which will include a new block and a new BIDX, and then changing B here with something won't affect the actual block in the grid from where you copied it from. So this is how it goes. So this is how you iterate, get each block, and then you can do whatever you want. So if I want to change the value 1 0 here, put something like this. So this is how you iterate over blocks and in a grid. Okay. So any questions here? There should be a lot of questions, but any specific questions to this part? I can remove. So what do you expect? So I've created only 2 blocks here, right? So I should be able to see which blocks are. Let's do that. Let's do a check. Let's say that I will output the BIDX of what you have created. It should be what? 0 and 2. Those are the only 2 BIDX which should come up in this for loop. Those have been created. So how do you do BIDX? So you have for loop.
We have not allocated now there.
So technically,
IDX will be able to.
Yeah, so let's IDX will be able to do. If you want to actually assign something to the grid parts, you have to do allocate first. So let's comment all these things. We'll come to let's just quickly run this code portion of the code once. Just to check again what happened. Killer. Oh, sorry. SSLABS killer. Maybe I should start using namespace. Trace. Error. Okay. So I'll just quickly turn it. Okay, let's turn debug on because we are doing a testing again. Very important, as we saw. Live demo. Major fail. BIDX is 2, BIDX is 0. Only those 2 are gone. As you can see, very interestingly, 2 came before 0. This is another very important thing you have to keep in mind when using these kind of iterator-based for loops in C++. These iterator-based for loops can randomly change the sequence of iteration. So don't use this if you want it to increment in an ascending order, decrement in an ascending order. Okay. It tries to randomly select pointer-wise whichever memory it has access to first. That need not be the incremental memory, usually. Access to fast, not first. First, it will be consecutive. That is not an issue. Faster. Okay. So just make sure of this. In SSLABS, the places where you need a certain hierarchy or a certain direction of flow in the for loop, you will have specific vector lists that will be given to you. For example, suppose you want to do multi-resolution simulations where you want to first update the finest resolution, then after 2 time steps of the finest resolution, you want to update the second finest resolution, and so on. So there's a very clear hierarchy that first the finest level, then the second finest, then the third finest, and so on, till the coarsest. So for that case, you will have something like coarsening L indices and grids and things like this, which are basically a ordered set of list, not an unordered random iterated thing like this. and you'll use that to iterate in a ascending order, descending order, and so on. Okay. So we'll come to multi-rate later on, not right now. Because that will be a one level extra problem. So now we'll create these blocks and see how to use multi-block thing. So let's say suppose we want to create all the blocks. Okay, we want to create all the blocks. So what will we do? We will just whatever blocks we have, we can create. See, for creating all the blocks, nothing to do. You have to use either you hand code everything or you can use that for loop. So this is the only time you will use the for loop. But if you're generating blocks conforming to a geometry and so on, the cat STL to marker function will do it in a more efficient way for you. It won't go over again this billion block metadata, loop over it. It'll do it in a different way. Okay, so that way it's fast. But here for small cases, I'll just do it like this so it's clear. I'll generate all the blocks. I plus 2, by plus plus. Technically, it should be std size t, but I'm being loose and fast with types here. Let's not do that actually. So correct. Here only in camp only it is incorrect, and in real world the heat of delivery deadlines it will go complete berserk. So bx and by. This is how you create the block. All the blocks are created. Now I'll go here and let's again do a check if all the blocks actually have been created. You should have 8 entries, 0 to 7. Oh, okay, 0 to 7, you have entries. Interestingly, here it has decided to do the reverse way of things. I don't know why. Okay, so now that we know that we have created all the blocks, what we'll do is for every created block, we will allocate memory for it. If you want to fill it with some initial value, you can fill it. Let's fill every block with the initial value of the boundary condition temperature, which is 80. And later on, we'll fill only the bulk part of it. Fill will basically fill every element. It doesn't care which is physical block, it just treats every entry as a legitimate entry, right? So every element is a legitimate element. Now we were doing get zone of a particular block, so we'll get the zone of this block. That's it. You reuse your block code itself here. Now what will we do? You're done with allocation of all the blocks. You're done with assignment of the bulk temperatures. Now we will just go and.
So B is that where you stored the data, is it? The first, the second.
Yeah, whatever is being allocated separately, it is basically telling you that there's a big chunk of data being allocated, so use it wisely. So B is basically being.
E is the index and B is the variable. Okay.
PIDX is the index, yeah.
Yeah.
So it is a flat
index. Yeah. I understood.
Okay. So now what we can do is we can now iterate over this thing and try to do this. If we do this, we won't get the correct result. No, okay, fine. Let's write it first. Why am I trying to predict that we won't get correct? Just because it's been hard. So again, we will iterate over all blocks which are present. Good. For all blocks which are present, we will just go to each block and we will go get the zone. By the way, wait, get the zone. Okay. So here is an example where we define the zone for each block. So let's define it here again. So we are iterating over each point inside each block in this case. Oh, by the way, I haven't created a grid for T new. So if this is the G block for T new, we will create a G new block. Or if you want to be really smart and optimize, you can do the copy paste blockwise. So let's not do that. Let's keep things simple right now. So basically, instead of creating a whole new grid of GNU, you can create a temporary BNU block here only, finish off your BNU equals B here, then reuse the BNU across all the blocks, all the Bs. Yeah, let's do that. That's a good example of how to optimize in the algorithm itself, not just by code and compilation and assembly and all those things. How you do optimization tricks in the algorithm. So we'll reuse it across all time steps. So what we'll do is, where's my scalar block definition? They delete it. I deleted it. Okay, fine. SSLABS, scalar block, E, D, and we have a BNU here, which is, we have num is my block size and numpad is my replica. Oh, by the way, yeah, now this reminds me. By default, all blocks which are created by the grid like this are not have a zero, are initialized to default values of other things that rmain, res, numpad also. Okay, so if you really want to set some value to that block, you should always do it explicitly and before allocating the full size. So before doing alloc, you should set your metadata. For example, if I want the numpad to be non-zero, it should be 1 for for a particular block. I should set numpad to that value what I want. Otherwise, it will take the default value of 0 and keep running with it. So when it allocates, it will allocate with 0 if you don't mention this explicitly. So numpad. Or in matrix blocks or vector blocks, the number of elements in the vector and so on have to be assigned here. So set num vars or set num groups and mems and so on. Okay. This is one thing you have to keep in mind. It won't complain if you don't set the numpad, because from the grid's perspective, it's fine. A grid without a pairing point is a steel grid or a block. What's the problem? But these stencil codes will start giving segmentation faults because you're trying to access something which is out of bounds. So this is your iteration over grid points inside a block, and here you can put your BNU. This will become B. All these will become B. Use temp replace with B, but let's not do that. I don't know what will change. Okay, so this is done. This is adapted. So this is the iteration over all the grid points for all the blocks. And now, once all the iteration over grid points is done, I'll use the same B mu to transfer to B. So this is one update of a block, and I'll do this for all the blocks. This is how you do the updates. Now, as you can see, it won't be correct because I'm not doing this extra transfer business. For this, I again have to write those, MPI send receive and all those. Fortunately, in SSLABS code, it's just a 2-line thing. You don't have to bother about MPI at all. We'll do it I'll show you how to do it. Let's first quickly print this and see what garbage it prints essentially. Okay. So actually, it won't print garbage. It'll just print the correct value because since we're not communicating any padding point values, no? All the padding points will have the boundary condition temperature. It's like you're simulating 8 clones of the same small system. Okay. So let's just try that once. And what we'll do is, to see that we're actually simulating 8 clones of the same system, we'll print all the 8 blocks in a grid and see whether the picture looks exactly like this. And each block should look the same, like high temperature diffusing gradually from the boundary to the inside. So we will keep this as a reference for the first block. Let's see. How do you address the first block? You say, you can use this thing. I think in the block thing, you even can use comma. Let me quickly check once, just 1 minute. Huh? So in the grid, a grid essentially inherits from a sparse T grid, which can give you, or at least Chakri wanted the syntax. So I was like, okay, I'll put it, but I never got to put it somewhere. I don't know. Operator tk. No, unfortunately, it uses only the vector syntax. Okay. So basically, the question was, should I put this also? The problem is they need to hand code for these separate unrolling things, and then you will get that d equals to 1 error again if you are not careful, if you keep copy pasting. That's why I said no more of that unrolling. Only for the minimum crucial performance critical cases I'll do that, not for this metadata stuff. Okay, so this is how you address the 0th block, which is this one, and the 0.00 of that block. So the first padding point, or the minimum most point. And if you want the first physical point, then you will address that block as this one, and then the first physical point. Okay, this is reference temperature. Now comes the fun part of writing a multi-block VTI or VTM. So marker will be the main file. Marker.vtm will contain the full grid structure, and the individual block data will be stored in marker_0.vti or something like that. It will have, so basically marker underscore is processor rank underscore PIDX. This is usually the syntax. It may not be PIDX, you can put some ID or something. I usually use PIDX. Okay. To make it distinguished, like for each processor, there might be multiple blocks. Like for example, in this processor, we have only one rank. We are not using MPI per se, so we are using only one rank, but we'll have multiple blocks. So open file with that PIDX. Now, where will I get PIDX from? We'll loop over all the blocks again, and we'll print all of them. So I'll open the file with PIDX, then I'll add the block, which is B. I'll add zone parrot. I'll add zone parrot. It's fine. Oh, if I add zone parrot, then it won't look. It will just look like a continuous thing. Okay, let's see how it looks. This is how you put. And now you have written only the VTI thing. How do you write the VTM thing also? So just copy paste. Just 2 lines. VTM writer is VTM, and VTI write, you just pass the VTI structure that you had. Communicator is usually, I think you don't need it. Check. There is a non-MPI version of VTM, because VTM is usually used as MPI. I wrote it only for MPI maybe. Just give me 1 minute. Huh? Oh, sorry. Good. SSLABS IO. Is there a function which takes only VTI? Yes, there is. Good. So we can use that. No need for MPI. So SSLABS VTM writer. VTM. Well, you can write it like this also. That's the reason why. You already use it multiple times. You'll pass the VTI which you were creating here, and that's it. Why like this? Why separate and why not together? Because people wanted to reuse this, put multiple VTIs, types of VTIs and all into a VTM. So that's why it was kept separate. Because you can put a constructor there itself, but okay, fine. So that's it. That should give me my grid of blocks. So let's run it and throw compilation error. Temp is not where 35. Oh, initialization. You know, it's a bit late, 2 o'clock. I think we'll quit now, and we'll come back at 3 o'clock for the scale market thing, or 3:30. Oh no! So people have that sprint and all. This is what
you can do the other things, but multi-grid, please wait for me.
Multi-grid? What do you say?
For multi-grid, please wait for me. Other
okay. Fine. No, you don't want SQL to market, is it? That brushes and all those things?
I have been using it. I don't need it.
Okay, fine. Take it. Multi-thread will do
Maybe-
so. Yeah.
Yeah, Karim. Thanks.
Okay.
So right now it is one processor multi-block, right?
Yes.
So if you have, so what I wanted to know was when you have different blocks like this, and it's always a rectangular grid, right? It's the domain is the domain is rectangular, cuboidal.
Yes. As in, you can delete a block. Like for example, I can delete this and keep it like this.
That is what. Okay. This is okay.
That is
So can you
handled.
group blocks like geometries, like?
That is what we'll see in the STL to market thing. How it is done
Nice.
automatically.
Yeah. Cool.
Yeah, because for example, if you look at you can show this pictures of your how the turbine blade is resolved with
Yeah.
blocks near the geometry and no block like inside or something. Yeah.
Yeah, we have seen, I think.
Yeah. I've seen that.
So we'll run this. And, oh God. Right. Did I not initialize something somewhere? Yeah. Tell me where. I did a BNU and forgot to initialize allocate for the BNU. Where is it? BNU. Where's my BNU? Here is my BNU. I'm back and I need to allocate.
This is you can even cover multi-grid because you are recording the sessions, so I can take from there.
I have to break at 220. So, okay, fine. We'll see how much quickly you can cover. Paraview, we'll open up, see what all files are here. See, you have created 8 VTI files and there is a marker.vtm. So if you open each VTI file, it will just show the block like we saw previously. Let's see what marker.vtm has. Let's first see what marker.vtm actually contains. It just contains a set of indices. So, why is there so many? It's indexed in a weird way. Oh, acha. Okay. This is the serial version of it. So, yeah, anyway, that's fine. This is why all these chota mota things I'll take care of later on. Let's see what it is. Oh, it's already open. Okay, so I don't know if you can see. I have to increase the thickness a bit. Opacity. This line thickness. Okay, we'll go to temperature itself. So temperature, as you can see, it's showing a thin outline of the blocks and it's overlapping because we have printed the padding points also. So as I was saying that in the spatial scheme of things, this padding point is basically a mirror of this. So it will basically overlap here. Like portion of the bulk grid here will overlap with the padding point here. That's why you see this outline of overlaps here. And so on. Now let's go to the actual surface values. And here you see you have a replica of those same systems. Now, why is it a replica? Why is there no communication here? Because obviously we are not explicitly told it to communicate anything across the blocks. It won't communicate. It's not AI. It won't try to figure out things for you and try to communicate and so on. So how do you do that? You don't have to write any other all those problematic MPI send receive blah blah and so on. And especially if you're doing without MPI, then where is the scope of MPI send receive? Then you have to write your own transfer functions. All those things you don't have to do. You just do 2 things. One is whenever you create a grid of blocks and you're done creating all the blocks, for example, when we are done creating here, you just tell the grid that please update your neighbor list or metadata of how many blocks you have, which blocks neighbor which block, and so on. It will do it automatically for you. So the function for that is update. So if you want the correct syntax, search here for update block enels. It's called update block enels. Okay. The g.update block. So it basically says update the block's nearest neighbor metadata among itself. Always remember to do this, because without this metadata, there is no the grid doesn't have any idea of what block lies next to itself. Because yes, it can generate idea, but this is a point where you say, okay, now is the time I am done creating all my blocks. Now generate the metadata. If you call this and then add some more blocks, please call this function again. It will regenerate the metadata again. So whatever blocks you have, if you want them to be properly communicated across each other and so on, the data, you always call this first before you use some communication technique. Now, what communication techniques can you use? The simplest one is, or the one which is currently there in the core library, which is the most useful one in terms of LB and finite difference and all these kind of things, is I will take this margin, or I'll take this margin of the physical block and copy it to the neighbor's padding point, neighboring block's padding point. So the function is just called that. Copy margins to SC NN pads. SCNN means if I am given a block here, I'll consider my neighboring blocks to be only up, down, left, right. If it's in 3D, front, back. I won't go diagonally and all. Okay, because that will consume more MPI communication location, like directions and so on. You can do that, but currently by default, because if you want to use this function, it wraps out the SC communications very nicely. You can write your own next nearest neighbor communications and all using the functions given here, but I have not wrapped it in a copy PCC NNNs or something like that, because there are a number of hundreds of combinations like this. So I've kept the simplest one. If you want something wrapped separately, customized for you, we can discuss, open issue. So what we do is, whenever we want to do this communication of the padding points across its neighbors from the margins to the SC, just call that function. So what is the signature of that function? You just pass the grid itself to that function. That's all. Very simple. See, no writing MPI send receive, no copy pasting also, no periodic nothing you have to do. Simple. So where do we use it? See, I need this for my stencil code. So I'll call it before my stencil code. And I'll be doing it at one shot across all blocks in the grid. So I will do it before I go into the individual block groups. Okay. So basically this will do it once every time step. Now let's compile the code. I'm pretty sure it will throw error. I can already see why, because I did not write SSLABS. Also, this might have a bug because I haven't updated this since August 2019, because no one uses non-MPI version of Communicate nowadays. So please forgive me. But what did I do? Why am I opening that? Compile. Oh. What? Oh, okay. Just give me 1 minute. This is the problem of 2D codes. Because no one is writing 2D codes, I don't specialize all these templates for 2D. Wait, just 1 minute. Let me check what the function is.
Somadip, you can make the main, all the like the arrays and everything quasi 3D, right? Just keep one dummy dimension so that you can avoid all that, right?
Use a bad example. Do that.
I'm not able. Some problem is there. Am I audible?
Yeah, you're audible. Yeah. Hello.
Yes, I'm saying that instead of.
Yeah, we heard. Yeah. That's what I'm doing.
Oh, okay.
So. And the second thing is the MPI business also. Yeah. Oh wait, what? Num blocks. Oh, two. Sorry, hard coded two. Hard coded somewhere. Second thing is this MPI business also. Quickly check. This again won't possibly compile because of that issue. That's actually not a 2D 3D issue. This is basically saying that I don't have a backscaler block. It's weird. I'm using it wrong. People who have used this function, can you please tell me what the correct argument for this is? Wait.
So for copy margins or what?
Yeah. For copy margins.
Yeah, so for that, it's the temperature and variable called com. Like I think the communication.
Oh, okay. So you're saying it has to use. I thought, okay, maybe I have not written the non-MPI version because again, no one uses non-MPI things. So, okay, I'll quickly put MPI thing here. So just MPI init as we did last time. The MPI finalize the dummy MPI thing so that we utilize the MPI syntax and MPI convert. That's it. Is it? Okay. Since we're doing this, we'll just use MPI convert here also. Otherwise, it will think it's using two separate functions. Yeah, that's it. So we are not running with MPI, we're just using the functionality. So, yeah, thanks. Again, generating a separate non-MPI version is so redundant and difficult. I just given up on keeping non-MPI code clean and updated. So let's run it as this thing only. What failed? 2D. Okay, some dimension issue. Wait, just 1 minute. Somewhere I'm calling a 2D thing. Where am I calling a 2D thing? Here. Beautiful. So now let's print. Let's see what the printer gives. Marker. Why do we call it marker? It should be technically called temperature, but okay, fine. Marker is a different thing altogether. So we'll look at the temperature field, outline, surface, beautiful. See, all the communication was taken care of automatically. Albeit we had to use MPI. If someone is interested in not using MPI and only using pure C++ code, please raise an issue. Whenever I get some time, I'll look into it. Because it's very redundant, like to. So okay. So this is the idea of using. This is a basic idea of using blocks, single resolution in SSLABS code. You would have heard a lot of this multi-resolution talk going on. Multi-resolution is basically where you have different. Again, going back to ParaView. Instead of a single resolution, you can have portions of. Marty, I'll show one of your pictures only. Wait.
Yeah, just a second.
I think I have one. Wait. I have one from the talk which we were giving recently. This one. Yeah. So, multi-resolution looks like this. Okay. So you have near the geometry, you have, so these are the grids, built into small blocks. You can almost see the blocks here, small blocks. Like so. As you can see, the spacing between two grid points here is large. As you go to the next thing, the spacing becomes much finer and then much finer till you can almost, it feels almost continuous and so on. So you have multiple resolutions in the same data structure, essentially. You do this basically because outside, away from the main area where the fancy physics is happening, you don't need to resolve so many complicated structures. Near the geometries where a lot of the aerodynamics happens, you need to resolve fine features a lot. with high resolution. So that one. Okay, so this is you can write the code for multi-resolution in SSLABS core syntax in just the same way like you did now, except that like we created a grid of blocks, now we will create a multi-grid of grids, which in turn contains a grid of blocks. Okay, so it's basically one extra layer of for loop. That's all. So here you will have a B coming out from G of B indices, and then on top of this you will have a for loop over levels of multi-resolution. So for auto, let's call it L, which means a level of your MG multi-grid, we will call L indices underscore grids, and your grid itself or a grid at a level L will basically be the L comma second, L dot second, because this is also a pair, so it's called a L pair, and this is usually called a B pair, which means a pair containing the B index and the block, and this one is a pair containing the level and the levels grid. So, okay. So this is multi-resolution, and instead of doing a grid, you do multi-grid here, roughly. And here you specify the number of levels you want. So basically, it's a list of, suppose I want resolution set 0, 1, 2, 3. I want 4 levels of multi-resolution coming in. It's exactly not like this. It's a vector of STD vector of level coordinates, because in the most general case, you can have rectangular grids. And if you have rectangular grids, doing multi-resolution in rectangular grids will mean that there will be a lot of compression along different axes. So you'll have full tensorial grid and so on. So the most general case is written like this, but the simpler, if you want to conceptually see it, it's just like this. You give the number of resolution levels. You specify the coarsest resolution here. The coarse resolution will be the broadest spacing or dx, and then it will accordingly keep doing coarse res or coarse res by 2, coarse res by 4, coarse res by 8. So 2 to the power of the levels that you have here. And that's it. That's all. Like, that's mostly multi-resolution. For the LB part, how do you use multi-resolution with LB? That someone with LB coding skills has to do, because there's a whole concept of coarse refill, fine refill, masks and so on, which is a bit involved. So someone who's, see, I forgot it ever since I wrote it in 2019. After that, I've completely forgotten about masks and all those. So I think Chakri is the only one using it right now regularly. So he's the best person to talk about.
Yeah, it's the best.
So please ping Chakri if you want to bootcamp on multi-resolution with the thing. The only small other thing I have remaining, I could really go now. Other thing I have remaining is still to marker, the geometry part. That will hardly take 30 minutes. So at 3:30 to 4, if anyone is free, you can join in. We'll just show how you generate things using STL to marker. Like, actually, you know what? Like, the simplest thing here is you can go to one of the examples here and quickly see what a STL to marker looks like. So you'll have a STL file, and these are all. How much time do I have? I think I can quickly generate a marker for you. So assets basically contains a lot of sample STLs. Huh? So if you open one called a torus, for example, it will show you torus. This is the STL of a torus. Huh? If you look at the data axis grid, it will tell you that it goes from 2.5 to minus 2.5 to 2.5 in each of the directions. And 2, okay. So 5, 2, 5, 5, 2 in real units. Its extents, lengths are. So I will just generate a marker for torus. So I'll go to STL to marker as an example. So essentially what it does is it will create a block with a scalar block, and it will try to say that, okay, any point inside the torus is going to be 0, any point outside is going to be 1, or ulta, any point outside is going to be 0, any point inside is going to be 1. And you create that marker grid, because for LBM you can't do direct simulations on the STL itself. You have to do it on grid points, because LBM is a point-based method. So how do you generate the marker point-based, like identifications, which component is inside which geometry and which is outside the geometry and so on. So essentially you have to create a grid of scalar blocks with the resolution blah blah blah. Brushes as a concept I'll come to at 3:30, and then you just call a single function, STL to BCC or SC marker, whatever you want. If you're doing a BCC grid, BCC marker, SC grid, SC marker. So you pass the STL file with STL units. In this case, we'll take it as 1 meter or something. And then you pass the marker grid that you created here. And pass the brushes. Brushes we'll talk about. Brushes are basically where you specify which region should have which resolution. Because if you want to, in a multi-resolution setting, or if you have an empty region in suppose the wake of a car, where you still want to create some blocks and analyze the physics, then you can use a brush to basically create a series of blocks. This brush basically is a brush for creating blocks. Okay, wherever you brush the grid with this brush, it will create blocks there essentially. Okay, that's it. So you can create. I can compile this code for you, and we'll see quickly how this works out. SLABS CAD.a, because we will need to include CAD also for this, and we'll change the test case here to use STL2 marker underscore SR.cd. Okay. Now, the way we run it is, Ravi, can you just quickly tell me what parameters should be here? So the first one is STL one, STL. That's it. So you pass the STL first. So torus, then resolution. So we will give a resolution of suppose 0.2 because it's 5. So we will block size we'll give 10 by 10 by 10 blocks we'll generate. We have it's 5. Okay, so as you can see, it generated 2 marker IDs at the end, which is basically representing there are 2 regions. One is inside the torus, one is outside the torus. If you want to see how it looks, the marker, again, you open the marker. Oh, sorry. I have to quickly go seriously. People will kill me. So surface is like this. As you can see, it has not generated blocks where it is not required. So for creating blocks here also, everywhere you need to use brushes. Otherwise, it will create only where geometry is there. And I can do a thresholding here, where I take only the grid points where the value is 1, which represents it is inside the geometry. If I apply, you see you have a rough course torus sitting here. It is broken like this because I'm not printing the padding points. If I print the padding points, it will be continuous. So this is how it creates a STL2 marker. Okay, so this will go into a bit more detail at 3:30. If people are free, you can join. Otherwise, join anyway. We'll have chats and you can ask all kinds of questions. Okay, so I really have to go now. Otherwise, my meeting will get cancelled and people will start calling. Okay, so I'll see you at 3:30. Whoever is free that time.
So, bye.
Okay,
Okay, bye.
Yes, you. Bye.
Bye.
Okay, see you.